I'm in the room, in the 318.
Okay, so I have a big question then.
Yeah, sure. Sure. Yeah, it's, you have about 13, how many minutes? Hello?
Good morning.
Morning.
I come with projectors and the microphones and all that, and just make sure here to make sure you all get hooked up.
Yep, I'm setting up my environment first, so just a minute.
And we're able to get on the Wi-Fi and all that.
Yeah, Wi-Fi is okay. Now I just need to check if my slides will go up. Oh, I need to update. Okay. Okay. So okay.
There we go.
Okay. Yeah.
Looking good. Do you have any videos or anything with sound you want to play?
No.
Excellent. Okay, just so you,
Very
so you're
simple.
aware,
Yeah.
is these are being recorded, so make sure you speak into the microphone, or if someone has a question, repeat.
Absolutely. We'll do that.
Okay, excellent.
And I should be good with that. No, okay. Let me make sure I have the right tab open. Okay, I will pull this over to another. um, Desktop. This over. Okay.
Second Ubuntu laptop we've had today.
Second?
Yeah, second.
Oh, okay. Okay.
All right, do you have any questions? You need anything else?
No, I
Ready
think
to
it
rock?
should be good. Yeah.
All right.
My collaborator will be here in a few minutes. And
Excellent. Did they have a different laptop or anything that's in the?
I don't believe he's going to use his own,
Okay.
but yeah, I'll call him and ask him to come. He's-
Okay,
Yeah.
absolutely.
Yeah.
I just like, just making sure all the laptops work. We've had
Right.
some.
Yeah, I think
displays
I,
work.
unless been having issues with my built-in Wi-Fi,
Mhm.
so I borrowed someone's, my folks'
Oh, perfect.
adapter, but everything seems to work now, so I won't disturb this.
Excellent.
Okay.
All right, I think we should
Thank
be
you.
good then.
Thank you. Hi, Pawan. Just come soon, huh? Because I have to give you some instructions. So you can keep this, you can take this off if you want to go. But only within these white lines is going to be recorded on that. But they will record the screen anyway. On my setup, it's just Ubuntu. This is Chrome. It's running. The additional things are here. I'll set it up.
And terminal is here.
And I have it. So if you just, sorry, I'll set it up. So Alt tab, this fellow. This is on the directory. Okay. So I made it so it's Alt tab is going to work. I think this font is big enough. Right? Are you able to see the fonts here? Is that visible enough? Big enough? Okay. Thank you. Okay.
Good morning. Very good. Very good. He didn't give me a I know I got good to me when I first got here. I'm putting myself in that category.
So hi everyone, it's 8. So I think we'll wait for about 5 minutes for folks in case there are a few people who straggle in. Is that okay? Thanks. ठीक है. So 8:05. No, I'll use this. Yeah, they don't. We can ask. If you ask one of them, they might have a pointer. If you really want a pointer. I used to have my own, but that thing is gone.
To change the instructions,
It's okay.
but I tested it.
You can change it live.
It's okay.
Okay. All right, Pawan, come. All right, so it's 8:05. I think we'll just get started. Let people come in later. So I'm Prabhu Ramachandran.
And I am Pawan Negi. Hello, everyone.
So I'm from the Department of Aerospace Engineering at IIT Bombay. So I've come in from India, and he's...
So I am a postdoctoral fellow at Illinois Tech, and I did my PhD. He was my supervisor at IIT Bombay, so that's why we are together.
Yeah. So welcome to this session. We'll get started. So I think I'll get things going. One of us will be around to, if you have any issues, to help you with any of this. So let's just get started. So both of us are computational scientists. We do a lot of numerical computation. That's how we got into this automation business at this point. So the outline of how this is going to go is as follows. I'll first give you an introduction to give you a backdrop of what this is about, what we're trying to do. Once that's done, we will jump straight in. So maybe about 15 to 20 minutes on the introduction. So if you have any big picture questions, comparisons with other tools, why this, why not, we'll discuss that. And then after that, we're just going to dive into it and just get started using the package. There are plenty of exercises. I will show you, we'll help you with installation if you have any such issues. But I hope you've already cloned the Git repositories for this tutorial. Does anyone need help with that? I'll put up the URL again, but if you haven't, you can. All of the material is available there. We'll get to that later. Okay, so I'm going to start here. So this is the backdrop for this entire workshop. It's this quotation, famous quotation by Buckheit and Donahoe, and they were paraphrasing John Clearbaut. So the point is, an article about computational science in a scientific publication is not the scholarship itself. It is merely advertising of the scholarship. The actual scholarship is the complete software development environment and the complete set of instructions which generated the figures. So this is a non-trivial quote in the sense that every time I look at a paper, I am reminded of this quotation, because we tend to look at papers as this body of truth. But in actuality, if you try to reproduce a paper, you realize that it's more of an advertisement than an actual, a document that you can reproduce. So it is really like an advertisement. So the paper is like an advertisement. But what's harder to obtain in most modern scientific computational research is the complete software development environment. Very often you'll find, even in reputed journals, barring ML and AI, where it's become necessary in some of the conferences, at least where you have to put up your source code, most traditional numerical methods computing do not care so much about reproducibility. Which means if you're trying to reproduce somebody else's paper, it's extremely hard because you don't have the source code, and very often you don't know the exact parameters. Okay, so this is a very interesting quotation made many years ago. So as I said, numerical method papers, so if you look at many of them, they require a lot of computation very often. Sometimes it's not of the order of days or weeks. It may be just a few minutes of computation. But very often for more sophisticated algorithms or complex algorithms, especially in the area of mechanics, you will end up having to do a lot of computations for a single publication. The second issue is, very often if you look at publications, even our own papers, there are mistakes, right? Because no one is actually going through your paper and saying, hey, this value here you have is wrong, it's inconsistent with what you're showing, because you probably type this up in a hurry, you run the code separately, you run this separately. So very often there are either missing parameters or actually wrong parameters. I've seen multiple papers where there are wrong parameters, and you write to the author, you can't get a response because they're too busy doing something else. It happens. I mean, I'm sure I'm to blame as well. Sometimes people write to me and I may not have the time to respond. The other issue is code availability. And this is not something this workshop is going to address at all. That's really the onus is on the authors of the software package. But when you have to do a lot of numerical computation, you end up with a lot of data. If you have, say, 100 simulations, you have the 100 simulation data, as well as the outputs from those simulations, all of those that you're going to generate. All of that data has to be managed in a fashion that you can make sense of. And it's not just that you make to make sense of it the instant or the time you're submitting the paper. Very often I don't know where you're all from. So maybe after this we'll do a round of introductions and you can maybe tell me where you're from. But at least in journals that I submit to, review times can be 3 months, 6 months, and I've had papers which have gone on for years. And so 1 year later to reproduce your own results when a reviewer says, hey, I want you to change this, is hard, especially in the context of so much data. So the goal that we are going for with this package is, can you reproduce your paper results after a year? Can you reproduce results of a colleague's paper in the same area? Obviously not in a completely different area, but in at least the same area, can you reproduce a colleague's paper? So that's what we're trying to do. And what we're saying is that Automan, which is a package we built out of this process in an effort to do this, is something that helps with this. Okay. So the goal of this workshop is to basically use Automan for your research, output, and publication. So during the workshop, we have, like, depending on how long we take, either an hour or half an hour, where we will encourage you to pick up one of your current publications that you're going to put out and automate that. So we'll sit with you and help you work with that. And the goal is, you want you to automate your manuscript to the point that every single figure in your manuscript, to the extent possible, is automatically generated. Which means there is a script, one single script that can generate all of these plots and execute all of your simulations and manage this whole thing. So that's the goal that we're trying to go towards. And hopefully at the end of this workshop, you will be in a position where you can do it yourselves. All right, so with this out of the way, I'm going to talk a little more. Maybe now that we have like 5 people, 6 people here, maybe we can do a round of introductions about what you work in so that we can tune things to your requirements. So maybe I'll start with myself and Pawan, and then we go from here. So basically, I work in computational numerical methods. So we work on, right now, on a method called the smooth particle hydrodynamics method, which uses particles to simulate mechanics problems. So if you have heard of computational fluid dynamics and computational structural mechanics, we do some of those computations. So it's very numerically intense. We have simulations that could take a few minutes to simulations that could take a month, right? And some that require a single core, and many that require as many cores as you can throw at it. So we can consume all the resources. So that's the area in which I broadly work in. So
I used to work in the same area as Mr. Prabhu, SPH, and then currently I'm working in machine learning based numerical methods. So in machine learning, we have to test it with different resolution, different network size, and we might have different kind of architecture
Pawan,
which we want to test.
you may want to come here. Otherwise, you won't be recorded. Yeah.
It will be the camera.
Yeah.
So we have to, I have to have like various parameters, and for that I have to do a lot of bookkeeping. So that's why I still use automan in my machine learning based methods.
Yeah. So maybe start from here.
I'm Andrew. I'm the head of data at an insurance startup called Dallas Insurance. We're based around a wildfire risk model to look for writing insurance for properties that are not able to get insurance now with the current ongoings with climate change and government politics.
Okay.
I'm Bindu. I work for the Texas Permanent School Fund, and mainly concerned right now with more macroeconomic research, mainly concerning GDP growth.
Okay.
I work with all genetic sequencing data. I use Python
Okay.
to do the genetic analysis.
Right.
I'm a grad student at Michigan State doing scattering experiments, and so one of what I do is data analysis on rich data sets.
Okay.
I'm Caesar. I work at UW's applied physics lab.
Fascinating.
I'm with SciPy. I'm working on 3D printing simulation. I'm still integrated with the student of motion industry students.
All right. Okay. So just to clarify, so do you have a lot of computational work that you end up, computational models that you run, simulate?
Most of a lot of my work, instead of making publications for academic, I have to make publications for private sector because we have partners in insurance,
Right.
consumers that have different reports. So we're using a lot of Python on my end for the analytics.
Okay.
We're using a lot of machine learning for the actual
Right.
risk modeling. And I think one of the challenges that we have is the developing of models is very complicated because we're using ensemble framework. We're not using just straight line framework for
Mm.
machine learning. So being able to replicate between the different
Ah.
research silos in like in a meaningful way and then get the documentation to be parallel.
That's hard.
My scientists are not very good graphics designers, so you can imagine how like if I try to compare results and it looks, I can't compare it because your graphs are too different. I'm sorry. So, although I'm hoping it's going to be a novel solution as a
Okay. All right. Thank you. So that's okay. That's very interesting. Yeah, because yeah, covered very different bases. So economics and genome sequencing and I guess experimental physics. Both of you. Yeah. Okay. All right. So we are not proposing automan necessarily as the be all end all that's going to solve all the world's problems. So anyway, so what we're going to require in this workshop is the following: basic knowledge of Python. The package is incredibly straightforward. It's a pure Python package. I don't think it has any dependencies on anything that needs to be compiled, except if you're going to do serious computation, you're going to have to do that anyway. So that's on you. That's up to you. So all our examples are all NumPy based, simple examples, in fact, they're very stupid examples just because we don't want to make it difficult that you don't get stuck in the example rather than. The only thing that we expect is that you understand how to write classes in Python, does anyone have an issue here with classes in Python? Okay, so I would assume that. And finally, comfort with using a command line interface. And we're not using Nabari or anything like that because it's so easy to set up. I would really want you to set it up by yourselves because then that's the whole point of this. So what does automan do? So first thing is it helps you organize your simulations. Again, so this comes from a very strongly numerical methods kind of context. So if that doesn't fit, we'll have to see how it works for you. It allows you to orchestrate running multiple simulations. Okay? And it also allows you to reuse your code for post-processing. And ultimately what it does let you do is it lets you generate all your simulations with one command. So you can just say, run Python automate or something like that. It will execute all the simulations for you, and then run all the post-processing for you and generate all of that output. Okay. And in the advanced section, we will be covering how you can add additional computational resources. Say in your lab, you have another machine you can SSH to, and it's free. You can just say add that. It will set up a Conda or a virtual environment for you there, and then execute your simulations there and pull back the results as and when it's finished. So this is what automan helps you do. And when we're going to get to using automan, we have 3 recommendations for you. The first is any program that you have. It doesn't have to be written in Python. It could be written in C. It could be written in Fortran or Julia, whatever else, or R. The only thing we expect is that it be configurable using command line arguments. And so that is our primary interface because that allows us to do anything we want with it. And if your original program doesn't do this, you can always write a Python wrapper on top of that with command line arguments to do whatever else. So for example, if you're running a tool like OpenFOAM or some simulation package which doesn't take command line arguments, but it expects an input file, you could always create a Python script that generates that input file and then runs that program. So that is a way by which you could pull it into this requirement. But our requirements are only these 3. That whatever program you have become configurable using command line arguments, that they generate output files in a directory specified on the command line. And this is crucial because when you have hundreds of simulations, there's no way you can do this in a reliable fashion unless you can configure where you're going to dump the output. The other way is, of course, you copy the file to another place and then you do that. But we expect this. And thirdly, this is a more common sense requirement, is that when you write your programs, write them in a way that you save all the post-process data. So if you're looking at ML models, you would make sure you dump your models. You save the models, don't just save the output of that. Right? Which is a common rookie mistake that we make. I mean, beginner researchers will say, okay, I've generated the plot, my simulation is done, but then you have to regenerate that simulation. It's a headache because it takes, usually for us, it takes an hour to do a simulation. And doing the post-processing is like a few seconds. So what we're trying to say is save the important work that you've spent an hour doing rather than just that final plot which takes a few seconds. So that's point number 3. So once you have this, you're kind of ready to use automan to do a bunch of things. So now comes the question that I have to answer very carefully, is why automan and not some other package? Right? So there are many other packages that do this, and we discovered this actually during the review process of this submission. I did a survey, I think, in 2018 when we created automan. I looked at a survey. At that point, there weren't that many packages. There was only one very good contender called Nextflow, but that was written in Java and was a little more complicated than I wanted, so I rolled up my sleeves and wrote my own. But if you look today, especially with the ML world being what it is, there are several tools that are geared towards ML model reproducibility and the kind of similar goals as automan has. So there's something called MLflow, there's something called guild.ai, there's something called Sacred, there's something called Neptune.ai. All of these are somewhat similar and they're somewhat different. Okay, so there are certain things that they are very good at. For example, Guild is a tool which you can use like Git. You can just install it and you can say Guild, run, and you look at your Python script, look for parameters, and then pull out those parameters, and then put them into a database, and then allow you to do visualizations of changes. So it does a lot of magic behind the scenes. So it's very powerful. And other tools are slightly different. They don't look at your scripts and stuff like that. But you have to explicitly say, here's a Python function. I want this to be captured, and it will sort of make sure that those parameter variations are captured and things like that. So they're all different. But automan in particular is designed for numerical methods, for the workflow that I'm talking about, which is you do a bunch of simulations, and then from those simulations you extract some results, and then you want to dump them into your manuscript. Right? So our goal is really to say, here's a manuscript, here are a set of figures that I need to produce, and we want complete end-to-end visibility of exactly what went into this figure, exact parameters that went into that figure. How did you generate the simulation? What are all the parameters that went into those simulations? And being able to play with all of that to do whatever post-processing you want. Right? So for a simple example, let's say you do, I guess everyone here understands quadrature, right? I have a function and I want to do an integration. And let's say you want to say, I want to look at the convergence of some new, I have a new quadrature rule that I'm setting up. I want to see how fast it converges. So you would probably have several runs that you make. This is of course a trivial example. You could do this in 20 lines of Python. But let's say I had something slightly more complex, like a larger simulation which takes 5 minutes. And you want to do 20 of those at different resolutions to look at the order of convergence of it. So one way of doing it with automan is you write the script. It does its thing. You run it with 5, 6 different invocations. It dumps output in 5 different directories. You write a little bit of post-processing that pulls all of this data and produces your convergence plot. And what automan will do is it will automate scheduling all of those simulations. It will run them for you. And then once the runs are finished, it will do the post-processing and dump the figure in your manuscript. So now you have a way by which you can just say, I run this command. It does everything else for you, and the figure is produced. And you have an explicit way by which you can say, okay, that figure was produced by this little script, this post-processing bit. This required these 5 simulations or 10 simulations or whatever. And so you have kind of end-to-end visibility of every parameter that went into a particular figure. Right? It's not a fancy interface, but if someone knows Python, they can actually dig up the details. So you can think about it as a makefile, like a makefile for building source code. This is like a makefile for your numerical research papers. The other thing about automan, which is maybe slightly different from others, is that it's non-intrusive. You don't have to change your code because we are using automan. Automan is like a makefile you write separately. The only thing is we expect those 3 things. Your script, your tool should be written in a way that it has a command line interface, it has, it saves its data, it saves its output to a directory that you can specify, and 3, that anything that needs to be post-processed is saved out rather than generating the plot by yourself in the tool. That's it. Okay, so the other thing very important is automan is also something that we know for a fact. We have about a dozen papers in our group which are fully automated. So I know for a fact that automan can be used to automate a full publication. With the other tools, I have not seen any evidence that they have fully automated papers or anything like that. So how does this work for us in our group? So I have several PhD students who've used this. I guess Pawan is one of them. So we have about a dozen automated papers. You can see the full source code of those papers, including the manuscript, LaTeX, everything. There are a bunch of repositories in that gitlab.com/piper. Each of those will have an set of either one or few automation scripts, which will produce every figure that's available in that manuscript. That paper is associated with. This has been done for both numerical research in SPH as well as for ML AI. So I have a couple of papers which use this for neural networks for PD simulations. And the nice thing is it's become something which some of my students at least automate by default. First time I suggested, why don't you try it? It's a bit of a pain first time. But once they got into it, they got hooked. So it's not something, it's kind of like Git. First time you do it, it's like, oh, I have to learn these 3 more commands. I have to remember to commit. I have to remember to do all of this stuff. There are these arcane commands you have to do and stuff like that. But once you do it, you realize that it kind of helps you a lot. So the same thing seems to have happened in our lab. And even though he's left the lab, he still continues to use automan. So the other thing is, I have found it personally useful because as a faculty member, I don't have the same time that a grad student has. My time is severely fragmented. So if I'm trying to publish something, it's really hard for me to manage multiple simulations. So using automan makes it easy to incrementally do research. So I can say, okay, here's this thing I'm working on, and then a month later I can come back to it and I still have exactly what I did before. Right? So it's easy for me to go back and make incremental improvements. And it's also easy to make changes. So 6 months later, if a reviewer says, hey, I don't like this plot, I want you to change this, I can just figure out exactly where to change it, run a single command and regenerate that one figure. Or if I say I want to remove this problem, I solve another benchmark problem, I could just throw a new in. So I have an exact way by which I can do that. So it's really convenient. And the other thing is our exploration. So if you're saying, look, I want to look at different methods, we usually drive this through automan. So we say, look, I want to look at convergence rate studies. I have a new method I'm proposing, but it's not fully convergent, so I'm tinkering. So I'll say, okay, do this, try this, run it, I'll look at the results and be like, okay, this doesn't work. Okay, fine, scratch, throw it away, try something else. So that's also something that automan fuels because I don't have to worry about, oh, I don't know what file I saved this in, I don't know which directory it's in, none of that. Everything is taken care of. So the bottom line is as follows. It says, it takes some effort to use automan. It's not free. It's not like, it's not magic. It's not AI or something. You can just show something at it and boom, it's automated. No, you have to spend some time doing it. But once you do it, later on, you will see the benefit of it. And then, just like version control, it's an investment you make, but the benefits are enormous. And I think the benefits are in some ways even better than Git. Because even if you don't use Git, you can use still automan to make sure that your simulations are taken care of. Right? All right. So one thing I want you to keep in mind, we are not trying to sell automan the tool here. Automan is a tool that works for us. What I would want for all of you to take away is the approach. So if you feel, look, automan stinks, okay, I don't like automan because it does this, it doesn't do this for me, it doesn't do that for me, at least take away the general principles that we are trying to cover here. And if you take those away, you can easily write one yourself. It's not a big deal. Automan is not a lot of code. You can use any other tool that works for you. But what we're going to cover is automan because we know automan very well. And we've used it multiple times to do this. Is that okay? So I'm just want to make sure that you don't think that I'm selling you automan. Automan is the means to an end. What I really think is important is understanding how to do the automation, how to think about automation, or how to think about publications, in a way that enforces this automation rather than the specifics of that particular tool. Okay? So I won't emphasize this again, but I just want to make it absolutely clear that I'm pretty sure there are certain things that automan is not going to do, because as far as I know, we're the only group using this tool. But we've used it for like 6 years now. 6 years we've been using this, and it does pretty much everything we've asked it. There are certain things we know we could add, but there's no end to that. But for multiple papers, it has worked, and it continues to do its job. So yes, there are certain things that may not work, but I believe that any of the other tools I talked about could, in principle, be modified or applied using the same ideas. All right. Okay, so now I'm done with the blah blah. Now we jump right in. So I'll switch to the second notebook. So this is the intro notebook. So we'll get started now. I guess so it's 8:30. So maybe another 15-20 minutes I'll hand over to you. Okay, so installation and instructions on how to get the material. Just install with pip install automan. I pushed a release last night. If you don't have it, that's fine. There were some small minor things that could have been fixed, which I fixed last night. Package works. And so if you have the old version, you should be able to just pip install -U. It should just update your version. So the latest release is 0.6. That's hot off the presses last night. But it is not mandatory. You do not need to install it right this minute. If you haven't, please do this. And I'm not going to say install this in a fresh virtual environment, because your fresh virtual environment may have nothing of use to you. So feel free to install this on a virtual environment that's of use to you. That would be my suggestion, because it has very minimum requirements. It requires maybe execnet or something like that, which just allows us to run simulations on other machines. So it's very minimal requirements. So I don't believe it should cause any major headaches for you in terms of installation. So I'll maybe give you 5 minutes to make sure you're all up to date, set up. We do use NumPy and Matplotlib. So in some of our examples. So when you run them, you may run into problems. So you can go ahead and install that with your favorite package manager. Right? This is not available on Conda as far as I know. I don't know if it's a Conda package, but it's such a simple package that it should be trivial to just install it with pip. I don't think it will violate any Conda hygiene by doing this. For the material itself, the material is on this long URL, github.com/Prabhu Ramachandran, first name / automan. It's on the website as well, so you can click this and get to this. You can clone this repository. There are 2 folders in this repository. Maybe I'll just quickly show you. So you see up there's code. This has all of the, right? So it has a bunch of examples. You don't have to go there right now. We will go there in a short while. And there's also slides. Slides has markdown files, which is what I use to edit, but I've also committed the Jupyter notebooks generated from those markdown files that you can use to see all the material that I'm presenting. Is that okay? So the notebook files, feel free to, you can load them up and work on those. That's fine. Okay. So just a show of hands, does anyone have issues with the installation? Do you need any help? We'll take 5 minutes now to make sure that you're all set up. So you can either set up a fresh environment or use an existing environment. Just do pip install automan and you should be good. So anyone need help? Because very soon, yeah, okay. If you want to test your installation, you can just do PyTest. If you have PyTest, hopefully you have PyTest installed. If you don't, okay, so if you've installed, you can install PyTest and then do PyTest minus minus pyargs automan. It'll run its test suite. We have about 80%, close to 90% coverage, so this should be, if you're good here, you should be fine. Okay, so do any one of you need help on the right side? You're okay? You're okay? You're okay. All right, great. Pawan, do you need a few minutes? Yeah, sure. Sir? Okay, so if you have this set up, let's get started then. So what we're going to look at is we're going to start with a very stupid example. It's really a toy example. All it does is it takes integers from 0 to whatever 10 or something like that, and takes the powers of it. So it's a stupid 5-line Python code, and it supports some command line arguments. Okay, so recollect that we have 3 requirements. It should be configurable using command line arguments. If it generates output files, it should do so in a directory that you can specify and control on the command line. And 3, any post-processing related output you want, you should save it in the form of data into a file rather than the output itself. That's 3 requirements. Okay, so let's look at our little toy example. If you run that cell, you should see the code. This is the full code, and the only useful thing is here, right? If I say compute powers of the integers up to R max and return the result. Okay, so it's really dumb. The reason it's dumb is not because we don't have more complicated examples. We just don't want to make it's not about the example, it's about how do you automate it. And so if you look at the command line arguments, I'm just using standard argparse. There are many other tools in the Python world for this. I was digging up a few. There are a whole bunch. So use anything that works for you. But argparse is the simplest, easiest, that doesn't add any more dependencies. So I've just picked argparse. Okay, and it's very straightforward. Usually you pick one of these examples, cut, paste, copy, modify. That's how you tend to do command line arguments. But there are some tools that make it a lot easier. You can just create a class, declare the types, and then say these are the command line arguments, and it'll take care of it. You put comments, it does a bunch of fancy stuff. But I've just done this most simple thing. All right. So you can choose to use anything else if that works for you. So here our command line arguments are as follows. You have an argument called minus minus power. You could also use the minus p option. That's fine. It's not a problem. But it's nicer to have the long version because then your variable names can be nicely named. So the first is the power. The default is 2. So it's going to give you the square of the integers. The second is the maximum, that is R max, from 0 to whatever number you want. And then there's an output dir, which is where if you're going to generate output, you're going to dump it, dumps it there. That's it. We compute this. And then the final thing is important. Given the output dir, it generates the 2 numpy arrays. It just saves that into a numpy compressed file. Is this fine? So this is like, I hope all of you are comfortable with this code. It's not doing anything important. The only thing that's probably, there's a lot more argument processing than actual numerical processing, but that's okay. Is that okay? And the only thing maybe people how many of you are not familiar with NumPy's saveZ function? Not familiar? Okay, so what it does is, given a file, it will save the arrays in a zip file essentially. Under the covers it's a zip file, and each array you give it is going to be a file inside that zip file. So when you load it, it gives you a dictionary like interface. When you load that, you can say np.load results.npz, and that will have a dictionary interface. So you say that object of x will give you the x array, object y will give you the y array. We'll show you an example very soon. Okay, that's all you need to know in this particular case. And then we run main. Is this fine? So your first exercise is going to be, find this example, it's in the code directory, run it and look at the output. Okay, that's not an exercise, but just explore it. So I'm going to do this here. So I go to the git clone of this, I say cd code, there is powers here, okay, powers.py. So let me run it. It's done because it had default arguments. So I can say powers minus minus help. You get all of these options. So I can say powers minus minus power is cube, and minus minus max is say 12. It's done. and now it has dumped this results.npz file here in this directory. Is that okay? Very simple. So I'll go back. Is everyone done with this? So now is your first exercise. We'll come around and help you. Generate the cube of integers. I've already solved this for you. Generate the cube of integers from 0 to 10. Plot the results generated in results.npz. You can do this right on the notebook. You just go generate this, cd appropriately, load the appropriate file, and then we'll see how this looks. So we'll walk around and help you. Maybe 5 minutes we take for this exercise. So if you need help, just raise your hands and we'll be there. Yeah. So if you're using the Jupyter notebook, beware the next has the solution. So I suggest not taking the solution first. The results time, exactly. So fine. So if you at least run if you've run the powers.py, I'll just walk through this because this is the base for all of the assignments that follow. So I'm just going to walk through this. So I've already run this here. So I just ran powers. Sorry, let me clear the screen. I just ran python powers.py minus power 3. That's the cube. I run till max 10. Or maybe I should run to max 11. Okay, doesn't matter. If I want to include 11, I don't know what I've written there. Now I need to plot it. So if I look in this directory, there's a results.npz. I didn't specify an output directory. So if I want to do that, I can say output dir /temp. It'll dump it in /temp. Okay, that's the only other thing that I've not shown you. Okay. So now how do I visualize it? I've put up matplotlib inline here. So I can say import numpy as np, import matplotlib.pyplot as plt. Then in my directory here, so maybe I'll add a so in the directory, so this is in the slides directory. So if I do data is np.load dot backslash code slash results dot npz. I'm going to just create a few cells here. So now this data object will have data dot, so let me do list of data dot keys. I have x and y, right? So remember if you looked at the example here, it says np.savez file name, x is equal to x, y is equal to y. So these are all keyword arguments, so you can call it anything you want. I could have said x a b, a is equal to x b, whatever it is. And each of those keys, corresponding to each of those keys, I have a file, and the interface is such that if I do data of x, it gives me an array like this. So this is the actual array of x values, and if I say data of y, that's the y values. Okay. So now all I need to do is plt.plot data of x and data of y, and I get my plot. Of course, I can embellish it with grid or labels and all of that stuff, but that's up to you. Is that okay? I just wanted to get this out of the way. Fine, so that's the solution we have. And the last thing I do here is, if you notice, the last line in this solution is plt.savefig, which just saves out the output. So presumably in your workflow, you have some massive simulation you're going to run. It could be a Python file, it could be something else. But you're going to run it, it's going to produce output in some directory. And then you're going to do some Python code, hopefully. Okay. This is no fun if you're not going to do post-processing in Python, right? So you're going to do the post-processing in Python, and then you're eventually going to save some output, and that's going to be the output you're going to either show or put in a manuscript or in a report, whatever it is. Okay. And that's going to be your savefig. So this is your basic workflow, and this is typically how a researcher typically starts. You write your code, you do your post-processing. Sometimes, unfortunately, the post-processing is in either a Jupyter notebook or it's on an IPython session. You generate the plot, and that's it. You don't have the post-processing code anymore. So what we're doing is we're saying, no, don't like writing tests. Don't throw that away. Retain that and automate this. Okay, that's the automation approach. Is that okay? So what do we want to do now? So now this is a toy thing. I just ran one thing. We made a plot. All good. But now what I want to do, typical scenario. So if this is all your paper had, a single simulation, please don't use automan. It's a waste of your time, right? So the reason this is important is you probably want to run hundreds of these simulations, and then you want to sort of extract some information from a bunch of these simulations and then make sense of that, or have a narrative or a story that you're going to narrate based on that. So in our little toy universe, we want to run powers with different arguments. So let's say this is the first time humanity has ever encountered exponents. Okay, we don't know how something to the power 2 is going to look or how it's going to look. So what we want to do is we want to run powers.py with a different bunch of arguments, different range or different order powers, exponents. And then we want to schedule all these computations, complete those simulations, and once all of those are done, I want to extract something and make a single plot that compares all the results. Okay. So this one is not going to look very nice because it's something very boring. The ranges are quite large. But this is just to mimic maybe a real world scenario that you may run into. And we didn't pick something from SPH because I don't want to inflict that on you. So, okay. So how do we now orchestrate this? How do we do this with automan? So what we will do is we will create an automate.py, which is just a suggested file name. You can choose to use any valid Python name that you want. Okay. Any Python file where you will write all of these instructions on what to run and how to post-process them. And the way we do this is by breaking up your task into what are called problems. So if you're doing, let's say you're doing ML. Do all of you have some ML background? Because that's usually the most common denominator today has become ML AI. So everybody here familiar with some ML machine learning? Okay. So let's say you want to run your network with different, neural network depth, different width, different activation function, whatnot, right? And you want different learning rates, you want to throw in different optimizers, and you want to choose the best optimizer that does the job or whatever it is. So what you want to do is you're going to run, a dozen simulations, and then you're going to look at, how the training loss or the testing error drops, right? And then decide which one you're going to use or something like that. So let's say you have, say, an MNIST problem, or your toy or your CIFAR 100 or CIFAR 10 or whatever it is, some image processing task, and you also have some other problems. So let's say you start with MNIST, you want to do CIFAR, and then you want to do fashion MNIST or something like that, right? So there are different data sets, and you say, I want to have this network that's going to detect, do classification, and each of those could be described as a specific problem. So you say one problem is CIFAR, one problem is MNIST, one problem is fashion MNIST or whatever, right? And so you break up your big set of tasks, your whole paper publication, into these little problems, each of which is a unit that makes sense to you. Okay? Those are called problems. And then in each problem, you specify what simulations you want to run for that specific problem, and all the different types of post-processing you want to do, however you want to do it. So let's say you make 100 runs and you say, I want these 50 to be plotted like that, these 3 to be plotted like this. All of that stuff is what you're going to do in that one problem. Okay? Once you've written that, all you do is you run python automate.py. You wait, take a coffee, take a break, run away, do whatever it is you have to do. Once it's done, you just come back, CD into your manuscript folder, of course, hopefully you've written the paper by this time, or maybe you're working on your paper when the simulations are running, and you do mkLatex minus PDF, boom, you have your paper. That's the goal that we want. Okay, does that give you a context of what we're trying to do here? You write your code, you've thought about what simulations you want to run, what problems you want to simulate, you break that up, put it in your automate script, and then you just say, hey, you run this for me, generate the output for me. And then you iterate on your manuscript. That's what we want to do. That's what we want to code. And if your problem is something that requires a lot more hardware resources, you should be in a position to add those resources. Okay? So that we will look at later. But for now, we will work within your hardware. So broadly, if you want to look at it pictorially, we have the following objects that you will see soon. We have what's called an automator. That's the automator that manages the whole thing. Internally, it has something called a task runner, which executes your tasks, and it has a scheduler. Both of those you do not have to touch, but what you do have to create is these problems. Okay, and the automator will create each of these problems, use the scheduler to execute all the simulations, and the simulation outputs will go into a specific directory, and the post-processed output will go into your manuscript outputs. Hopefully you have a manuscript/figures directory. This is what we tend to use. You can use anything you want, and you dump all the output into that. Okay. So the basic idea is the simulation output. So there are two things. When you run powers, it generates a results.npz, right? That is not something you want to put into your manuscript. The manuscript only cares about your final, what did we have here? xcube.png or whatever, right? So you want that manuscript file to be here, and you want the results.npz file to be in the simulation outputs, and we segregate these two. Is that okay? Does that make sense? Okay. So the simulation directory has simulation outputs. The output directory is the manuscript output, which is your figures. And as I said, we break up the simulations into groups called problems, and each problem can require any number of simulations that you want. Hundreds, thousands, tens, whatever it is. Now each problem, as I said, manages a set of simulations. Each simulation has its own outputs, and you will post-process those outputs using whatever Python you want, and then you will dump that content. So all of this part is stuff that you will write. Automan is not going to do this for you. So as I said, Automan gives you this sort of framework to break down your manuscript or your report into these pieces, and once you do that, 80% of the problem is done, the rest of it is just detail. And so Automan manages the detail in a specific way. Is that okay? In principle, you could do this with Dask, you could do this with MLflow or whatever else. Okay, so let's look at the simplest possible, not simplest possible, but a very simple automate that we have for this specific problem that we started with. So let's go over this. I'm going to walk through this line by line. Is that okay? Okay, so we have a bunch of imports. The most important here are problem, automator, simulation. All of these you have seen in the last few slides. So there's an automator class, there's a simulator class, and there's a simulation class, and there's a problem class. The second two imports are entirely up to you. If you want to use BQplot or some other plotting tool, go for it. That's up to you. Same way you can use Xarray instead of NumPy, not my problem. You do whatever it is that loads your data files, that's entirely up to you. Okay, we have just chosen to use matplotlib and NumPy. Then comes the first problem specification, but ignore that for now. Look at the main block. So in the main block, we have instantiated the automator. You will probably have to just keep copying this every time you do it. This is just you just see this once, copy this main block for the future, and you should be good to go. So I'll just explain what it does. So this is the automator which drives the entire simulation. You pass it two arguments. Simulation dir is where all the outputs of the simulations will go. Here I have defaulted to outputs. This is what we tend to use. So if I'm synchronizing files between two machines, I ignore outputs because outputs is like huge amount of data I don't want to backup. Manuscript/figures is where all my figures go. Okay? And the nice thing is, when we split the problem into different problems, each problem gets its own specific directory inside which all the simulations reside. The same holds for your outputs. So in manuscript outputs, you'll have a directory corresponding to that problem. So it's easy for you to navigate. Is that okay? This will become clear when we run this. Okay? So as I said, automator has two things that you specify. The first is the simulation output. Where do all the simulation files go? The second is where do all the manuscript outputs, as in your report outputs, where do they go? And the third is the set of problems you want it to execute. And here you specify these as classes. You just say, give me problem powers. And then you say automator.run. Okay, that's it. So now, as I said, the only thing you'll probably need to change here is this. What are the problems that you want? You'll have to keep adding here. Okay. So automan avoids doing things like magic. Everything is explicit. So it's not like, so in principle, I could have found all the problem instances inside this file, automatically run all of that. We don't want to do that because we want you to know, we want you to be fully in control of what you want to do. Okay. All right. So the first thing is the powers is a problem. So we have class powers derives from problem. And it has a method called setup, which is always called for you. And what we expect in this setup is that you set up this set of cases that you want to run with a list of simulations that you want to execute. As many as you want to do. Okay, so here we have a single simulation which takes the simulation, it is given a directory root, and we call it 1. We want x to the power 1 in this. And the base command is just the command you want to execute. So you could execute anything you want. It could be a C program, R program, Perl program, okay, anything you want, Fortran code. Okay. And any of the arguments you see following that, I say power is equal to 1. Keyword arguments are automatically converted to command line arguments that are invoked on the executable that you pass. The only thing to keep in mind here is, if you notice the base command, it has an output dir. $output dir is the only magic that we have, which automatically injects the appropriate directory based on which simulation you are running. So let me explain the context. I'm going to make, say, 100 simulations with powers. Each simulation is going to have to go into its own directory, and I need to manage this. So I don't need to worry about this. I just say $output dir, and automan will figure out which file, which class you've been set this up in, and based on the root of that simulation, it will create a directory and dump it into that. Is that clear? So So here I have a single simulation which just done this. Now the second method that you keep in mind here is called run. This run is not running your problem. All it does is after your simulations complete, it will execute this function. And right now all it does is makes the output directory. That's all it does. It makes an output directory. It doesn't make a single plot, nothing. So all you will get is in manuscript you will get a new directory, nothing else. Okay. So now let's run this and see what it does. So hang on. Okay. Actually no, maybe I'll go with the flow here. I won't disrupt the flow here. I'll come back to running this. So just note the first thing, the automator instance and its arguments, three arguments. The first is simulation dir, output dir, I don't even remember, output dir, and all the problems you want to run. Three things. The setup method is a method that gets called for every problem, and that's where you set up all the cases. So self.cases should be a list of simulations that you want to run. And then the output dir output dir is automatically determined and injected for you when you use this. Okay, I have not shown you this. So if you notice here, there's a self.simulation path 1. So if you look at root, simulation has the first argument is root is simulation, self.simulation dir. So the problem class has a method called simulation dir, which basically gives you a subdirectory inside that problem. So it's just a convenience so that you don't have to find out, oh, I'm running in this problem. So let's say you have a simulation and you want to say I cut paste this case and I want to run it somewhere else. You can just copy paste it somewhere else, but you don't want this output not to be in that directory but in the other. So you don't hard code anything in this case. All your hard coding is that simulation path 1 there. Okay, so it's inside a subdirectory. Some of this will be a little clearer as we proceed. So now I'll focus on the simulation instances because it's the most important thing you'll be looking at. So why do we have to do simulation? Why couldn't I just say, strings, Python, powers.py, minus minus power 1, minus minus power 2 and put all of these 10 commands. So the thing we have found is very often you have multiple parameters. This is a toy example. We have only 2 parameters. So if you have 30 parameters, it's very hard to figure out, and run this. And then once you have run all of these, I want to say, give me all those things which have only power is 1. Give me all the cases that have power is 2. You can't do those things too easily. You can do it, but it's a bit of a pain. So simulation instances allow you to manage the parameters. It allows filtering of these cases. It also allows you to specify the number of cores or the number of threads you want to execute this thing in. It also automatically converts any keyword arguments to command line arguments. And it also lets you render these keyword arguments, command line arguments in your matplotlib plots. So if you say, look, I have a parameter called alpha, but I want it to show us the Greek letter alpha whenever I do plots, you can have it do this for you. So you can, one of the methods is render quark. You just re-implement that and then add whatever it is and it will take care of that for you. So some of this is driven by you. So you can subclass simulation and make your own simulation to do whatever it is that you want to do. Right? So if you have a specific tool that you're running, say genome processing package, and you say that the simulations of this always behave in this particular way, you can create a special instance of subclass which does whatever it has to do. Okay? So basically the control of what you want to do for a specific type of simulation can be done with that. Okay. So let's quickly look at simulation just to understand how it works. So notice that at this point, just because I have a simulation, it's not going to execute this simulation. Simulation is more like a placeholder so that we have all the information necessary for a particular simulation. It doesn't execute anything at this point. So I've just imported simulation and I've created one which says root is test. I've given it some stupid base command. And I have given it an argument, one argument saying arg underscore 1 is 1, arg 2 is b. Okay. So now if I were to look at s.name, this is a property which will be test. It will be the last directory of this root. So for example, if I did It will still be test. So it cares about the last directory in the root path. Okay, I'll leave it as what it was. Okay, maybe I'll keep it as this. Okay, so now we look at the command. So what is the command that gets executed? Test minus d dollar output dir minus arg1 minus arg2. So the dollar output dir is still not substituted. It's substituted only at the end when it actually gets executed. But notice that arg1, arg underscore 1 here has become arg1, arg equal to 1 here. So it has changed underscores to dashes because that's the Unix convention. If you do not want this, you can change this. There's a single method in simulation. I think it is called s dot coags to command line. Okay, so if you look at this implementation, there's a method which, so you can do whatever you want. You can just return the command line argument, it will take care of it. You can remove the first two and take it. Okay, so right now what it does is it converts anything with a dash to an underscore. Okay, so it's up to you. You can do whatever you want. The default does this. If you just use a plain old simulation, anything with underscores will get converted to a hyphen in your command line argument. Is that okay so far? So good? The next thing is the useful one. S.params will be a dictionary with the keys as your arguments and the values as whatever you have passed. It's just the coags at the end of this. Not a big deal. Now these two are very useful. S.input path, notice what it says. It says it's SciPy test results.mpz. Is that okay? Okay, and the last thing is render parameter arg1. In this case, we have not said do anything specific. Sorry, not arg1, arg underscore 1. So if I wanted to put a label for this quantity, right now it's going to just show up as arg1 equal to 1. If I overload that method to say, no, show me arg1 as beta plus alpha, whatever, some Greek character, you can always do that here. Okay, that's just another method. Now if you notice this code here, I said root is self.simulation path. So simulation path encodes the directory in which this particular problem is running. Does that make sense? So if I have a simulation just has a root which is a directory basically. Now I don't know which directory I'm going to be running in this particular simulation case because this simulation is now part of a problem. So there's a method in the problem which basically says this is the directory in which this problem is executing. All of this indirection is just to give you a way by which you have a very clear way to describe each simulation has a specific directory in which it's going to run. All of that comes from which problem it is in and which simulation it's in. That's it. Is that okay? So again, the model is you have a set of problems. Each problem gets its own directory. Inside that directory, you have a bunch of simulations, and those simulations each have their own directories, right? So you have a hierarchy, and that hierarchy follows from the code here. And the reason you get that is by using a simulation path. If you use simulation path, what it does is it says, oh, I'm powers. This is the powers problem. So my subdirectory is powers, and anything after that will be that particular problem. So in this case, it will be powers/1 will be the subdirectory in which it executes. This is okay? Fine. Okay, so now we come to the fun part. Now you've learned pretty much significant bit of automan. So now let's run this. So I'm going to run Python automate 0.py. Okay, so it started. So it takes some time. The scheduler takes every second. It doesn't do it super fast because it waits for 2 seconds before everything executes and stuff. So that's it. So everything ran. So what it did was the following. It said it started a worker on the local host. It ran this job. And then after it ran, it did a post processing which did the plot. but we did no plot, right? We didn't write any plotting code, so nothing should have been done. So let's now see what are the outputs in this directory. So now notice there are two new directories. There's a manuscript directory and there's an output directory. So let me look at outputs. Outputs now has a powers directory, which has a 1 directory, which has the following. It has a job info.json. Maybe let's cat that. Let me cd into this. Job info.json. That gives you info. It's a JSON file, so you can load it with anything. It says job started at this time, ended at this time, status was done, exit code was 0, so it exited cleanly, there was no errors, and that was the process ID when it ran. So it has some basic information about the execution. Results.npz is what we had. Automan also captures anything in the standard error and the standard output. So if you did a print statement, it will go into stdout. So if you just want to print stuff and find out what you printed, you can do that too. You can go back and load this file. Is that okay? So we're done. So now let's see what the manuscripts file are at. Okay, cd minus. Manuscript figures again has a powers directory, but it has no output because I did not make any output. I only created the output directory. Right? So if you remember, this is what we did. That run block has nothing inside it. Is that okay? But now what did automan do for us? It ran this simulation for us. That's all it did. So it seems like an awful lot to do just to type Python powers, right? But just bear with us. You'll see why this is fun. Okay, so now comes your exercise. So make some plots. Start with the automate 0.py. Modify it to produce a plot in the run method. And I suggest 2 hints here. First is use simulation.input path to locate files in the simulation output. Right? So if you remember, the input path will be powers/1, right? Now you don't want to write, never hard code something like this. So you simply say self.input path results.npz. That will give you the right path that it needs. Is that okay? Does that make sense? So now you've avoided having to deal with where this directory is and stuff like that. You just say self.input path. Okay, and remember all your cases, the case information is in self.cases. So you can pick all the cases from there and do whatever you want to do. Now if you want to output a file, you want to save the plot, you use self.output path. Is that okay? Okay, so I'll give you about 10 minutes and I think we'll take a break. Do you want a break now or you want to take a break after we finish this exercise? After? Okay, fine. So we'll finish this and then you can take a break in an hour and 15 minutes. So. Okay. So if you have any questions, just raise your hands, we'll be there. I guess you were able to complete the plotting.
Yeah, we need 5 more minutes.
5 more minutes. Okay.
Everyone done? Yeah. You're doing it. Maybe we just walk around.
So if you have completed the post processing, okay, 2 more minutes. Yeah, almost. Yeah, he's done.
Just give me 2 minutes.
Okay.
So we take a break now,
Yeah, we can take a break.
and then come back to this one.
Yeah. So we'll take a 5 minutes break and then 10 minutes break. Okay.
But we're supposed to give a 10 minutes.
Yeah.
Then
So
we have breakfast. So you decide. I mean, so these are 5 hours. You want 5 minutes, 10 minutes? 5 minutes is enough? How long the break would you like? Okay. So 10 minutes? Okay, we take a break for 10 minutes.
ran into the good problem.
ये रिसर्च को कोई ऑटोमेट नहीं करने वाला है.
so many parts of it, like we are actually having to scale back the domain of like what are you trying to predict towards, and like trying to figure out where machine learning methods and stochastic methods kind of intersect in terms of like the improving predictive powers. Yeah. Right. That's the problem. So no, but like we are trying to take so a lot of what we're trying to do with the machine learning is to kind of better account for the randomness of stochastic methods. So like because the actual value of the disaster is not in the randomness but in the tail. So you're not so we're trying to force exactly, and that's like but that's the problem with stochastic method, right? Because stochastic method relies on the randomness of the domain. So what we're trying to do is we're trying to use machine learning to take out a lot, or like we're trying to reduce the domain in a way that takes out a lot of the randomness and focuses on the peril as it relates to what's important to like the business. So it's like so myself, I am the actual client, which is it's a very strange relationship. Like typically what you do as a risk modeler is risk modelers are typically vendors. So like a client, as an insurance person, you would hire a risk modeler. We are actually internal in the company, so so we actually can do some fun things in terms of like skipping process because we don't have to produce. But the quote unquote client is just the market cap for us. So all we have to do is we just have to ensure that we can skip a lot of steps in terms of like reproducibility and in terms of like uncertainties because all we have to do is maintain bottom line in terms of the outcome for our quote unquote client ourselves. Because the actual product that we sell is an insurance product. It sells itself because nobody can get insurance right now. It's easy. But like the client, the opportunity for us is the ability to write without actually incurring risk. So if anything, the problem is the easy solve would be just not write wildfire at all, right? That would be the absolute, and then you don't write anything. You write in the middle of the city, no trees, and then but then that's overfitting the problem statement. You have no margin. So like we're chipping away at uncertainty. But like once we it's a standard home insurance, yeah, just a standard home insurance, right? And then we're going into commercial and other things. So like it's a very unique. I think the position that I have is very unique. I don't think many other people would have as expensive a domain, especially like now because I started as the risk modeler, but as the company expanded and like got into the actual business, like full on business of scale, now I'm like department head and not only in charge of environmental risk, but actually business risk. So that's something now like it's interesting. Yeah.
Are you modeling it via are you when you say reduce the sort of variability, are you doing this via Bayesian methods or?
So if you're talking about spread and actual event simulation, the team on the research side is actually using Bayesian methods to do spread and simulation like that. We are actually removing the statistics as much as possible because what we're looking for is a maximum case.
Yeah.
So we're reducing the domain of trying to remove as much randomness as possible, looking at maximum case of event. So, for example, Bayesian, like the standard statistical model, sorry, single.
It's okay.
But it's like basically you have a tree, if it ignites, what is the chance of the entire tree being on fire, half the tree on fire, whatever, like that. So then you have that in your simulation model. The question that we're trying to answer with machine learning is, that is a tree, and the confluence of conditions means the maximum fire size is X. So we don't care about the randomness. It could, but we only care about the tail of the event. So we're reducing the domain only to the tail. And only to, but like in a smart way, because again, you have so many covariates and so many different resolutions in terms of remote sensing
probability of code failure.
Correct. Yeah. So, but you're going at it from, but you can't say absolute worst, because like if you say, well, every tree is therefore on fire. That is
No, obviously,
right.
sometimes that would be too conservative.
Correct.
So that's why stochastic is there. So
Right. So there's still elements of statistics involved with it, but it's very much more of actual art than it is math right now. Like you have to understand the interactions between layers. You have to understand the interactions of the push and pull of like what is the different machine learning methods that you're doing, because we actually have to model model more in the frame of multidimensionality than actually two-dimensionality. So typically what people do is they stack and point. So like you take a stack and you try to flatten the stack into 2 dimensions, and then you have a certain risk because you reduce it into statistics. We actually think that it has to be approached from multiple sides. So if you have elevation as a layer, your interaction of elevation with wind, or your interaction with elevation with vegetation health is actually different. So you actually have to include elevation at multiple points in the model instead of at a singular point in the model. So you actually have to approach it. So that's why the ensemble, we call it the ensemble methodology instead of just a standard machine learning methodology system. Where you model.
But you will still use an estimator that tells you what's the worst case.
That is correct. And like
So you're essentially saying that you're still using a probabilistic model for your
for the core,
you're using some estimator that gives you still probabilistic.
right, the heart of it, that's again where the ensemble idea comes from, because like you also, not only are doing that, but you have to create, you have wind surface, and the wind surface has the uncertainty. You have a downscaling plus your real surface plus your downscaling surface, and you have this uncertainty interaction with that. And then you have your temporal reductions, because you have hourly winds, but that doesn't represent climatically, yearly climatic changes and shifts. So you have to reduce multiple domains and multiple scales, and like trying to balance all of that is strange and unhealthy.
But it is a sort of, are you searching? Is this a search thing that you're doing?
So we tried to do as a search where we got the capital to do like the dumbest approach to machine learning, where you create the data lake and you just run search through the entire thing and interactions with the entire thing, and it failed miserably.
And when you were searching, this is when you were using your Bayesian sort of optimization.
Yeah, the whole grid search, the whole like all the different like variable like hyperparameterizations of the lake, and then it just fails because you actually have to create intermediate data product in order to, again, like you're trying to reduce. If you're thinking about it as a 2-dimensional domain, that makes sense. If you're doing a search and you're just trying to find optimal conditions in a bound domain, but like we're trying to understand, well, this domain is actually not firmly established. There's other information that has to be combined in novel ways before you actually reach the finalized endpoint of wildfire risk. So it's a very strange space, and it's like again the mix of art and actual math inside there, because just by looking, if you ever look at a wildfire model and you ask how do they put in actual climate condition, so if you have a wildfire, you have wind as a driver, but wind by itself is not modeled correctly. Wind that you see on Doppler radar is atmospheric, 10 meters, measured 10 meters above the ground, validated and interpolated between weather stations with stochastic method, right? So that's already a terrible surface, because you're not even considering the downscale effects of like what is the slope doing for the wind at the top of the rig.
looks like you have a lot of parameters.
Sorry. And that's where something
I
like
think,
this makes you
yeah. Okay, let's get back to the workshop. It's okay. So let's look at the solution. The next slide is just the entire solution.
Just use less.
Okay. Okay, so everything else is same, except this is 2. Yeah. Yeah, so here you should note that to access the output files, we have used case.input, right? And everything else is same as we do any kind of plot. We can access the x and y data, and we can put a suitable label to that. And then all other cosmetic changes, like we want to put a grid and put a label and legend. And at the end, at savefig, there is something, the second thing that we have given you as a hint, that you can use self.output path to access the output folder, which is the manuscript figure. So let's see. Yeah. So as in the previous slides, we have seen that in simulations, you can also access params. So here, to set the label, we have accessed the case.params, and here we have power, which we have set here in the simulation. So we can access that and put a suitable label to that, so what that plot corresponds to. So everything else remains same. Then let's run this. So it didn't run. So what we want from automan is, let's say you have run a very large simulation, and we don't want to rerun those simulations. So that's why automan never runs a simulation which has been run before. And second thing is, it also doesn't overwrite any of the post-processed files. But sometimes you want to make some changes to your post-processing. So let's say you wanted to change the label, or you wanted to change the file name. You change that, and you can forcefully post-process that. So there is a -f option where you force it to rewrite the post-processed data. So first, let's see. Okay, let me run this. So now you can see the difference that earlier in the last run it didn't run anything, and now it had run this powers problem. And let's see what the output is. So the output directory remains the same. Outputs, powers, and only one folder. And these are the outputs. In powers also you can see there is only one output. And inside the manuscript folder, there is figures, and only one folder. Inside that you can see there is one file, which is the plot. The plot is same as you have generated. So in case you want to rerun some simulations, you have to manually delete it. So we have not provided any function which can delete your output, because we don't want automan to delete it. It should be a conscious decision to delete the output folder, delete any simulation, and then rerun it. So if you want to delete any simulation, you can delete it by accessing it manually. So let's say just this simulation I want to remove. And then we can rerun it. So now when the simulation folder is, the output folder is absent, then in that case we can run it without -f. I think we have to, yeah. So if the output folder, the figures, the post-processed data is there, then it doesn't run anything. But if it's there, then we have to run it with -f option, and it will rerun the. It's not running. I think it didn't delete the output. Oh, it removed. Okay. So now it's rerunning the simulations. So two things to note, that it never post-process any data which already has an output. So if there is a folder created with names figures, powers, then it won't post-process it. And second thing, automan does not have any functionality to remove your simulation data. So if you want to remove your simulation data, you have to manually remove it and then rerun it. So let's get back to the exercise. So here what I just discussed, that if you after applying your changes to the post processing, if you directly run Python automan 0.py, it won't run, and then you have to use this minus of the option that just deletes your post processing data. So here is the solution that I discussed. Now this is another exercise where you right now we were just running one simulation where there is this argument where we have set power equal to 1. Now let's say you want to run a lot of simulations where you want to compute x to power 1 to x to power 5. So how do we do that? Using automan. So take your automan 1.py and edit it to include those options. So let's see how we do it. So okay, so but it's not that straightforward, that's why. So basically I can just give you a hint that you have to create a different simulation for each power. So inside the self dot cases, the list will be 5 different simulations. So you can use a for loop or use a yeah. So just do. So this is an exercise. You can. I can give you 5 minutes to just do this.
So I just want to make one observation. So if you do Python automate.py minus help, see there are lots of options. One of which is you don't have to just run all the problems. You can choose to run a specific problem. So you can say Python automate 1.py powers. In this case, we just have one, so it's okay. But if you have like 5 or 10 different ones, you can just choose one and it'll just execute that. And the simulations for just that. So you can use minus help. We haven't explained it here, but that's okay. Yeah, so please carry on. So 5 minutes. It shouldn't take you too long. Again, the idea is just create all the simulation instances. And then now the only thing is you're plotting. You again have to do a little bit of work for the plotting. If you want to plot all of them together in the same plot. So ideally we'd like one plot which has all of these plots in the same plot. So it's probably just like 5 lines of modification.
Yeah.
It's not
So
too much. Just 5 minutes?
Yeah.
Okay.
So while plotting, you will feel that why these two commands are helpful, especially the first one, that simulation dot input path. So you can loop through all your cases and do case dot input path to access the results.npz file of that particular simulation, and then keep on plotting in the same plot, and then create a single plot for all the simulations. Okay, so let me show the solution.
Just go back next. Go to previous.
Okay. Yeah, so here you can see. Oh, this is not the one.
Sorry.
Mhm. Yeah, this is the one.
No, it should be
Two, yeah. Okay. So to create different simulations, we have used this for loop for all the parameters you want. So this is a simple integer parameter, so that's why we can just use this loop. So from
this combination.
yeah, list combination, and so here the range is from 1 to 5 because we want the arguments from 1 to 5, and this will create the list of simulations for us.
But I guess 5 will not be included, so exclusive.
5, yeah, 5 will be excluded. Okay, yeah. So it should be 6, yes. Okay, and when we are plotting, we want, so it's the post process is something that depends upon the use case. So here we want to show that how these powers we want to compare all these powers, right? So for that, we want to create a single figure which takes data from all the simulations and then plot it. So we can use the similar code, but here we have to access all the cases. So here we cannot hard code the path. So that's why this case.input path is helpful. And then we load all the data and then use the same command to plot as we have done before, to plot all the plots in a single plot. But here notice that this case.param, this is also helpful because this is giving us the particular value of the power argument that we have passed to that particular simulation. And then everything else remains the same, and we can save this and get our one plot which has all the variation of powers. Okay, so let's run this.
No, don't run it here.
Okay, so
Let's go there. Go to the tab.
okay.
Tab.
So first we have to remove the old outputs. So in this case, we don't require to remove the old outputs because the power 1 is going to remain the same simulation, and other simulation are going to create new folders in the same directory. Automate 2. So we have to override the post processing because there's already one post process file created. So when we do -f, it's going to run all the simulations which has not been run. So this is not running extra power 5 because the change is not there in the main file which we are running right now. So you'll get this kind of plot, right? So let's have some observations. So all the cases which we have already run, the automan does not rerun them. So for example, in this last file that we have run, the case with power equal to 1, it did not run. So we can go back and see in the terminal this one. Which one? This one.
No, the white one.
Okay, sorry. Yeah, so here you can see power equal to 4, 3 and 2, these simulation run, but power equal to 1 folder was already there, all the data was already there, so it did not run that particular simulation. So and as we have seen that it automatically runs all the cases for you, and you have to use -f when there is a post-processed file and there is a folder created for that. Then you have to use -f option to recreate that post-processing, and if you have added any additional simulation, it will first run those simulations and then post-process them. Right? And here we have used, we have assumed that generally post-processing is very quick compared to doing the simulation. So that's why automan also does not give you a convenience to delete all the simulation outputs. So here is the summary of the workflow, that you have to create problems. So each problems, you have to create multiple problems, and each problem can have multiple simulations. And generally, for a single problem, you want to post-process them together. Right? So all the simulations, you can choose what you want to post-process, but for a problem, our post-processing is, the post-processing is created in a single directory. Right? And simulation has a lot of conveniences that you can use to access the output folder, the input folder, and the parameters. Yeah, and automan manages how, where it has to run the simulations, all the scheduling and all. Automan does that for you. So I think we can move to the next part.
Thanks, Pawan. So I think I'll take the next session. So we're done with this. The next is going to be 03, which is parameter sweeps. So let me. Okay, so in principle, we've covered bulk of the core features of automan. So actually, this is enough to get to automate like whole set of papers. But in practice, you will find that it can become a little tedious, especially when you have like hundreds of simulations, right? Because in all of these, we have done manual specification of, okay, for loop here, these are the arguments, passing those arguments. So here we just had one argument, which is power. So that was easy because you just say for list comprehension, for loop, and it spits out, it's just straightforward. But supposing you have like 5, 6 options, which is common in ML. Right? So you may have activation function, depth, width, epochs, and learning rate or whatever, right? So you have at least 5 right on the top of my head. So in those cases, it becomes much harder to do this. You can't just do a single for loop anymore. So automan provides some very convenient tools to generate these parameters and utilize them in this workflow. Okay, so it's using this takes again some getting used to because you have to think in this fashion, but it's fairly straightforward once you get the hang of it and very convenient. So there are 2 main functions that we provide which allow you to generate a huge number of options. So the first is called mdict. I ran out of names. I thought mdict was the most appropriate for the reasons that you will see below. And the second function is called dprod, which is a product of 2 dictionaries. We'll talk about this. Okay, but the easiest way to learn this is through example. So I'm not going to talk about theory at this point. I'm just going to talk about the examples. So the 2 things that you need to import will be from automan API, import mdict and dprod. And now we'll start looking at this. So my first case is a numerical simulation case where I have 2 parameters, nx, which actually represents the resolution along x, along a specific direction, and 2 Reynolds numbers. I don't know if everyone's familiar with Reynolds numbers here, but I guess the physicists here will know about this. But there are 2 parameters. There's a parameter, it has 2 numbers in this case, 100 and 200. You may have any other numbers, that's fine. So now what I want is, I want a simulation with nx is 10, but RE is 100, nx is 10, RE is 200, nx is 20, RE is 100, nx is 20, RE is 200. So essentially I want the product of these 2. So what mdict does is, for every keyword argument you supply, you give it a list. It will take the product of these lists and return a list of dictionaries with those keys. So let's just run this and it'll become obvious. So this gives me a list of dictionaries, each dictionary having the corresponding options, which is nx is 10, nx is 100. So it's very straightforward, but it's remarkably powerful what you can do with just this. Okay, so it's trivial to generate. Like, I can now put one more if you want, right? So I can say, so we have an exercise here. So maybe we do this as an exercise. So given 3 parameters, n which we want values 5, 10, 15, order which is in 1, 2, 3, and func which is some function which is either sine or Gaussian. Generate the product of each of these as a list of dictionaries using mdict. So you can try your hand at this. You want to try? So it should just be mdict. N is equal to 1 to, no, 5, 10, 15. Order is 3 and func okay, I'm just going to be lazy. That's it. So, and notice that they all obviously don't have to be the same length. You can have one which is just a single parameter, but don't do something like this. Okay. Quiz question. What will this do? How many options will I get? No, you will get 27. So it will treat that as an iterable. So it's going to treat that as an iterable. So you're going to get sin. So if you want sine, you need to put that in a list. So, right?
I guess internally should check for its
Well, because this is a use case. I may have options A, B, C, and I want to do this. I don't know. So it does the minimum possible. No fuss. So, yeah. Anyway, you'll find out when it runs the simulation. Yeah. But it doesn't do any checks. It's going to treat this as an iterable and it's going to iterate over each of those and do the product of those. Is that fine? So this is like super convenient to do this. Okay. So this is what mdict does. So okay, this is that solution. So we get this. That's done. But now sometimes you have something more complex, right? So here is the following example. So let's say I have the nx and re values that I wanted. 10, 20. 100, 200. Okay, so that's 4 sets of parameters. But now if you're doing ML, you may have, say, for example, Adam optimizers, learning rates are very different from BGFS, BFGS, LBFGS, right? So if you say Adam I want to use, but Adam I want 2 learning rates, 1e minus 2, 1e minus 3, but I want 1 and 0.1 for LBFGS, right? So now I can use mdict for these 2 optimizer cases. And since there's lists, I can add them, right? So I can do create an mdict, get a set of options, another mdict, add these 2. I get a list of the sum of these 2. But now I have a list of dictionaries and another list of dictionaries, and I want the product of these 2. Does it make sense? So I want nx is 10, nx is 20, re is 100, re is 200, with all of these possible optimizer combinations. So now you can no longer do this with mdict, right? So dprod this is where dprod comes in. It takes 2 of these combinations and does a product of these 2, right? So if I did this and then run that, I get all of these. Does that make sense? So when you have combinations that you want to group together, you use mdict, generate those. Generate as many of these, and then you can do products with anything else. So now you can, of course, I can do more of these. I can now have this list, and I have one more set of options. So you can now explode your number of cases. It's very easy to set this up, and it's just like 2-3 lines of code. Is that okay? So I found that this is like, it's a little mind-blowing, but it can generate a huge number of options. Is this okay? Any questions? Okay. So the key operating idea here is we generate a list of dictionaries. Okay, so you can see where this is going. So now comes the next major problem. So for every one of these cases, I need a unique directory to dump this data into. So this is a pain if you want to do it by hand. So we have another convenience method called ops to path. So whatever options you have, it will spit out a path, suitable path name, right, which does this for you. So here I'm going to show you again by example. So I'm going to look at ops to path for all ops. I'll just show the first three. I'm going to get the first three, otherwise I have like too many. So what it does is, learning rate is whatever, nx is 10, Adam, optimizer, re is this. Right? So if it's a string option, it won't say that option name, comma this, it'll actually put the string option. So it generates some sensible, reasonable directory name that you can use. Does it make sense? So now you have a way to generate a bazillion different options, and you have a way by which you can encode this into a directory, which makes sense. So you could even read it by yourselves when you're walking your directory tree, and that's it. So right, so does that. Now very often you may have so many options that you don't want to encode all of them in your directory name. Otherwise you'll have a directory name that's long, right? So ops to path has several options. So you can say only look at these keys. You can give it a list of keys, or you can do the reverse. You can say ignore these keys. You either specify a positive set that you want to include, or you specify a negative, which is don't include these names, and it will not include those keys. And you can also give it a map. Map the key names through this dictionary. So you have if you have a key name that you don't want to show up here, and you want to map it to something else so that the directory name is more consistent with some other structure that you have, you can give it a dictionary and it will map it through that. Okay, and there are examples for each of these. Is that okay? So you can look at the docs for this. This is like, it's unlikely you'll need this, but if you do, you know that you have some of these options. And if you look at the code, it's not very complicated. You can generate this yourself. So you can take that code, rip it out, do whatever you want. Is that okay? So now we have a mechanism by which you can generate a lot of options, and now you have another mechanism with which you can generate unique directory names for each of those options. Okay, so in summary, we have these three methods, mdict, dprod, and ops to path, and now you are in a position to generate as many simulation instances which don't, fight with each other. So now I give you a bigger exercise. So look at the code polyfit. This is again a very simple example which takes NumPy, generates a bunch of points, fits a polynomial to this set of points with polynomials of different order. So it has some 3 or 4 command line options. So you start with the automate polyfit, modify it to perform the fit for different order polynomials from 1 to 8, and compare the training and test error. So I want one plot which has the training error versus order, test error versus order, nicely labeled. So this is your exercise. Is that clear? And please use all of the things that you have at your disposal. Right? You can use mdict, you can use okay, I'll give you 10 minutes for this. Is that okay? You want me to go through polyfit? So here I'm just looking at the sign function. Maybe bycat. Okay. So here I have no, this is not Vim, right? Yeah, okay, this is better, fine. So all it's doing is, it's fitting, you give it entrain, enttest, give it some noise, give it an order, and you pick a distribution for your noise that you're picking from either uniform or normal, it just generates a polyfit with NumPy, and then computes the training error and the testing error, and dumps all the output in this results.npz file. And it also dumps a little plot in the same output directory called plot.png. Okay, so this is typical in a simulation. Simulation will do something, compute some output, and also dump something. Right, so you have only individual plots, but now you want to look across these and then look at the training error across these. So, and here are all the command line arguments for it. So it has 1, 2, okay, significant ones are 1, 2, 3, 4, 5. So 5 different command line arguments excluding the output dir. So you can imagine this can start getting a little more complex, but it's more manageable when you start using automan. So yeah, so I'll give you about 10 minutes to at least try this, or 5 minutes. How are we doing on time? Oh, so it's now 2.5 hours. So do you want to try this, or do you want me to just go to the solution? It's not particularly hard. How many of you would like to try? You want to try? So 5 minutes? Okay, fine. So I'll wait for 5 minutes, and then we'll wrap up with the solution. Okay, so maybe we'll just go through this because I have a couple of more sessions. We have an advanced section with how do you add additional resources and stuff like that. I want enough time for that. Okay, so let me just quickly show you the solution. Automate. So it's already there in this case, polyfit solution. Okay, so I've not changed much. I've only changed stuff inside here. Oops, sorry, what did I do? So I've used opts here. Is mdict order is range 1 to 9. I wanted 1 to 8. So I'm using range here. So that's it. It's just a single parameter. There's nothing much here. Doesn't matter. There's a subsequent exercise which does more. But this is just an example to show you how you use mdict. Now the key problem here is how do you generate or use these options in your list comprehension. So the way we do it is we use keyword argument expansion, right? So I say simulation root is whatever, and I use ops to path here for each option. Right? So notice here this line. So I start with for opt in opts. So every option is so that is a dictionary. So OPT is now a dictionary, and now I just pass that to ops to path, and it spits out a directory name. I can just blindly use that. Base command doesn't change, and all the options are now I just say star opt, and it's done. So this is the convenience of doing this. So all of this actually is built so that you can do things like this. And now you can see why this is very convenient. I don't have to actually change this code a lot. I just need to generate the right set of options, and I'm done. So that's it. So the setup really hasn't changed too much. We only started using command line arguments and keyword processing.
But indict is not necessary in this case.
Sorry?
Indict is not necessary.
It's not necessary. In this case, absolutely not necessary. But if I didn't use mdict, I couldn't use ops to path, and I couldn't do star opt. The nice thing with mdict in this case is if I have additional arguments, I don't change any of this code. I can just say mdict order range 1 to 9, comma, whatever else. Ntrain is this, ntest is this, and use this. I could just explode the number of options, and none of my setup code would change. Whereas if I didn't use mdict, I would have to do everything manually. So this is the baby step, first baby step. But yes, great question. Now we come to the run method, and this is just nothing major. I have saved out all the orders. So I'm going to have a list for order, list for test errors, list for train errors, and then I just iterate over each case, load the file, append the parameter order because I want to do order versus test error, training error, load the data, test error and train error. This of course requires that you study polyfit and understand what's dumped, which in your simulations you would know that. And then we just do a plot, give it appropriate labels, and we're done. Is that okay? So now if I were to just, any questions? So the key here is, again, notice here nothing has really changed from our previous example. The run method isn't really changing. We're just using case, input path, self.output path, and params. That's all we're doing here. So we try to abstract it out in terms of case related parameters. And the only key conceptually new things here are the options and how we generate them and how we use those options dictionaries in our instantiation of simulations. That's it. So now let me run this. Notice in this case, there was no output. Still, manuscript output is what it's dumping it into. But yeah, so I didn't have to worry about running this, naming it. All of that is completely eliminated for me. If I had to do the same task manually, or even if I was writing the code in pure Python, I will have to reinvent the wheel basically, right? I'll have to write my own ops to path. I'll have to do all of this argument processing. I'll have to split. So whereas the nice thing with automan is it gives you this framework. You just break it up into problems, split it up this way, generate your options, go, right? So it becomes this, muscle memory at some point. So now if I look at, it's going to be a mess, but let me see, manuscript, figures, this is not powers, this is polyfit, errors. Okay, and that's our training and test error. Not bad. Right, and it's not a lot of code. It's once you put it into this framework, it's automate, polyfit solution. So this is like 58 lines of code which does all of this stuff. And as I explained, I could have done hundreds of these. It's not an issue. Okay, so that brings us to the end of parameter sweeps. I'll finish the next and then you take over advanced. Okay, so now we switch to the fourth session, which is filtering and comparisons. What do you want to do? I think advanced, I'll try to run through this. Okay, fine. Okay, so the last basic part before the advanced is some plotting utilities to make things easier when you start having a huge number of these simulations. And this is again entirely optional. In fact, with 3 you're good to go, barring the advanced material. So I find that this sometimes works, sometimes doesn't work because it's an automated way of doing plots. And sometimes if you're doing manuscripts, you want a lot more control than an automated plot. So in those cases, you're going to have to abandon this and do a brute force way. But this is nice when you're doing exploration and you want to just say, okay, I have these parameters. I want to do a parameter sweep. I want to quickly generate a bunch of plots that give me an idea of what's going on. So that's where it's useful. So 2 major tasks. The first is I want to filter out some cases. So I have say 100 cases and I want to say, give me only a subset of these cases and do a plot for those cases. So how do you filter those cases? There are very straightforward methods to help you with that. The second is I have, again, a set of simulations, a subset of those, of which I want to do a similar plot for every one. So let's say I want to do a line plot, and I have it for 5 different orders of my polynomial. I want to do all of them, put them on the same plot. So it's the same plotting code. I just have to read from different files. And I want to label them based on parameters in the file. So it's going to be very repetitive coding. So there's one method that we have which allows you to do this with the minimum amount of repetition. So you just write one plotting routine and it will automatically generate it for all the cases that you supply. So in order to do this and make it easy to follow, I've just created an example where we have a bunch of dummy cases, okay, which there's no backing data for this, but there's just a bunch of cases that we have here. So I'm going to run that, and now we have 12 cases that we have that we will use as examples to play with, right? So all of these are calling polyfit with 2 of the arguments. 1, 2, 3, 4 is the order, and ntrain is 10, 20, and 30, right? So 2 parameters. I could always expand this out, but it's messy. So first, if I want to filter cases specifically by name, right? That's the most stupid thing you can want. It's very unlikely you'll want it, but I have found in some papers I want to say, I want to plot that one simulation. The only problem is you need to remember that mouthful that you have here, but there can be a smarter way to do this, but this is what we have right now. So you give it a list of names that you want, it will pull out those and give you those. This can be written in probably 1 line of a list comprehension, right? You can iterate over all the cases, iterate over all the names, check if this matches that. That's really what it's doing. But it's just a convenience called filter by name. The next is I want to filter cases by a specific parameter, right? So I want to say, give me all the cases which have ntrain is 10. So this will do that. And then you can say, give me all the cases that have ntrain is 10 and order 3. You can do that. I'll give you one particular simulation. Is that okay? So you can do this with as many parameters as you want. You can also filter with a function, again straightforward. So you give it the set of cases, and then you give it a function. In this case, it's a lambda. And then here, for example, I want all the even functions. No, sorry, all the odd functions, all the odd orders. Sorry, right? So it'll give me all the odd orders. Of course, you can make this more complicated by giving params. Order is this, but ntrain is 10. So in fact, this is way more general than the previous case where I explicitly say parameter names. But it's also you need to learn how to write a lambda function or a function. Use whatever works. So this is just the names of these, just to show that I did indeed get the odd orders. So now we're done with filtering functions. So now you have all the cases. You can do filtering of them and get subsets. Now comes the slightly more complicated part, which is doing automated plots. And so here's an example. So first line here is just a bunch of imports. All I have is matplotlib inline, importing numpy and matplotlib. And I have this function from automan API called compare runs. Okay. So I have a bunch of runs, simulations. I want to be able to compare them. And in this particular case, I am looking at a very numerical methods example where I have an exact solution. It's optional. So if I don't specify an exact solution, it will not plot that. But very often you say, I want this and I want to see what's the correct answer or something like that. So the exact in this case is just doing NP cosine. It's nonsense in this case, but it's just a plot. So just show you something. Okay. So it just does x is NP linspace and then just does this. Usually you will have something which is relevant to that particular case. So for example, if you have an exact solution for a problem, it may depend on a specific parameter in a case. So you may have a case specific exact solution. So you can pull out, you will get the case and then you can use that case parameter to generate that. Is that okay? Because the argument passed to this exact will be, the first argument will be the case. The second argument will be a set of keyword arguments for any plots that you want. So if you notice, when I do plt.plot, it has the star keyword arguments padded on. So if those are passed, they will be used. So the exact is like a occasional case. More often you'll be using the main plot function. So here what we're doing is, I am looking at the order and I'm generating y is np.sin w times x. W is the order. Okay. This is complete garbage. But you may do something else. You may load a file and do whatever it is that you have to do there. And then I'm just plotting it, but I'm plotting, this is very important, that you pass the keyword arguments here because things like the line style, labels are automatically generated for you in this case. So what you need to focus on is, I have some data I want to plot, you focus on your plots and that's all you need to do in this plotter. So now what I'm going to do is, I'm going to pick out all the ntrain cases. Okay. So I filter cases, given the same old cases that I generated. look at ntrain is 10. And then I'm going to compare the runs for these cases. So the first argument you see is all the cases. The second argument is the plotter function. The plotter function will be called with every case with a fresh set of keyword arguments corresponding to whatever you cycle. Yeah, we cycle through line styles and stuff. And then I say, don't label every single thing, right? So I have 5 parameters. I have order, I have noise, I have the distribution that's used, I have ntrain and ntest. Now if I put a label like that for everything, it's a mess, right? I only want to look at order because I'll write the rest in a caption or whatever. So I want to say label only by order, and that's it. And then do plot legend. So now notice what it does. Sorry, I didn't run this. Now this plot is a mess because I have so many cases, right?
Case thing is not used, I guess.
I'm sorry?
Case thing. The one that's filtered those cases. Filter cases.
Yeah.
It's not includes anywhere.
But absolutely right. That's why it's a mess.
It's
Case 10, yes. Thank you. Yes, so this looks good. Yeah. It's order 1, 2, 3, and 4. But now the problem is this, right? The legend placement is automatic. So if you want, I did just legend here, you can change that. But notice that the line styles are entirely automatic. I didn't pick blue or green or, so you may have a more sensible, way of plotting this. This is not going to help you in that case. So you may have to do a little more fine tuning. And doing that for this is a little mind bending because you're calling this fellow that, your compare runs is doing the dirty work for you. And so it can become a pain to do this. So very often I find that most of the students in the lab don't use compare runs because it's too mind bending to manipulate, and they just handwrite whatever for loops that they want. And usually that works because it's easier for even someone who's reading the paper. Otherwise this is like magic. It's like, oh, okay, you ran this and it's going to do something. But it is very convenient when you want, because it took me literally like do the plots, and now I can reuse those plotter functions for anything I want, for as many plots that I want. But the actual plotting, barring those functions, is like 2 lines. Like it's 1 line basically, right? Compare runs and plot legend. So it's a power tool, but it, like with every power tool, you got to use it with care. So
It's good for development phase.
yeah, so when you're developing and you're saying, look, I want to look at losses, I want to see all of the losses in one shot, then you say, okay, I'll look at it. Right. But there are ways by which you can tweak the line styles if you don't like the defaults. This is the default. So all we do is we use iter tools, and for all sims is the cases that we have. It just generates the product of black, K is black, blue, green, red, and minus is line, dash is dash line, and then dash dot, and then dot dot. So it sort of cycles through all of those. Kind of dumb, but it's nice for plots. But if you want something with more colors, you can use this instead, which is black, blue, green, red, Y, cyan, and magenta. And if you want to do more, you can. So if you want to say, I don't have lines, but I have markers, and I want to do different markers, you can use this. So these are all pulled from our examples. You can use any of these. And you can pass styles to so if you look at the arguments to compare sims, the last argument is styles, which is this function. So you can pass it those styles, and it will cycle through those styles. So you can use this for what it's worth. Your mileage may vary, of course. Right? So you can play with these slides for inspiration if you want to copy paste and use in your plots. So the last exercise, which I don't think we will do, I don't even have a solution for this, as in it's not a big deal, is update the automate polyfit to make the plots, use filter, and compare runs to generate your plots. Right? So it's an exercise, but I'll leave this as a homework exercise, and we will move on to the advanced section because I think now it is close to 3 hours. So I think next half an hour we'll finish that. So the plan is as follows. we'll finish the advanced section, and then if you want a break now, we can take a break now for 5-10 minutes. Like a break? 5 minutes, okay. Let's do a 5-minute break. We'll come back for advanced. And after advanced, I would like it if you can work on your stuff, and we'll help you to automate your stuff, because we've covered it. Okay, see you in 5 minutes. We'll reconvene at 10:53. Okay. I'll set it up. Pawan, 1 sec. I'll come with you.
That's a really interesting solution. You come up with automan.
Hmm.
I'm not 100% sure how I'm going to put it. If I can use automan direct, but I like the framework that you've provided here, and like the ideology of like applying this to your department. I think that's very inspiring.
No, thank you.
Yeah. So yeah, we're looking into
It
different.
seems it's very simple, but it's just grown out of our needs. Not like super familiar, but we have like, close to 15 papers we have fully automated.
That's awesome. Yeah, because especially we're getting into the business of scaling machine learning and research in machine learning spaces. So like it's yeah, this is coming out of need for the company. It's like I can do this, but I'm now managing like 50 different versions of this and different directions of the model. So
Yeah.
it becomes a pain.
So some of the model version stuff I think we check out.
Like DVC is what we're looking at, the data version control.
Ah,
Yeah.
okay, yeah.
So like that's yeah. So we're it's
So we don't, I mean, we see version control as a layer orthogonal to this. So
I'm
we
just
do
thinking that
this-
too, yeah.
Yeah, so we put this in a Git repository and then we commit every time we change the automan.
Right.
And in fact, when we do papers, if it's, I make the simulations, then I do the simulations.
Yeah.
And then I just share my figures with him,
Right.
so that he can run anything he wants to run, but otherwise he can just make a manuscript whenever he wants, and I just send him a zip file every so often.
Yeah.
It's dirty, maybe we should use DVC for that, but that's a bit too much work.
Yeah.
It's fine. But yeah, we see this as completely autonomous tool, so we don't do provenance of, where, oh, this changed in my source code, and we don't track source code.
Correct.
Change your source code and your results have to change.
Right.
We don't tap that. So that's a bit, that's too much big brother watching.
Yeah, no, it's interesting to me because I'm implementing scale right now. So like I'm choosing the direction of like, oh, is a tool like automan like a good fit? And like is something like DVC interacting with automan like a good fit? Like so.
Yeah, because it's autonomous, I think it shouldn't have a problem.
Right.
But I think you need more protocols, or either you have something overarching, either a set of rules for people to play with.
Yeah.
Saying, okay, do this and then do this, or have a framework which is taking care of that.
Well, this also like helps me kind of communicate to the software. Like if we need to involve the development team into like building something similar to automan, like
Yeah.
what's the targets?
Yeah.
Or like
Because I don't see this as, there wasn't any other tool that made this,
Yeah.
which was easy enough to write, but then now for advanced stuff, I'm like, I develop a UI for this, or
that's literally everything I'm doing in work too. It's like there's nothing exists with this, so I have to create the packages myself.
but there are some there are ideas from Gil,
Yeah.
flows, have nice, some of them have nice web UI stuff.
They look
But
nice,
They look nice, but I don't know if they pan out for a full publication.
I'm afraid of anything that has a UI, an UX right now. Like like a UI, like a GUI. I'm afraid of anything that has a GUI.
No,
right
they
now.
all, you have to drive them from the
Yeah.
code, and they're like
Post processing, as in the what's happening to your code base, it's showing it.
it's actually pretty nice. So for example, if you have
big as it is, it's one very small piece of our puzzle. So that's where production reporting is actually sometimes more important for us. The stakeholder investment is like, oh, this is the direction of the models and the direction we're going, and here's the publications we're doing, etc.
So for us, it's a modest and research paper on arguments. It fits that niche pretty well.
I think that this is like, yeah, I can see it, again, architecture-wise, I might have to deploy like several instances of this for the different reporting functionality I have, but I think that this is a...
Or you could use this as a base to build a fancier too.
Exactly. That's what I'm thinking.
But that's the thing, for us it was, can be the realization like the very, like bringing this as a framework, as an idea, to do this, and it's a good way of managing the stuff, is itself, I think, a big thing.
Yeah.
Automan is just a detail. This is an implementation.
Yeah,
I
that's
said this is more okay, there's a way to think about the simulations to make it easy.
I like that. That's, I mean, that's precisely the reason I joined this session, was to learn about the mentality that you had going into the creation of Automan.
Yes.
Or do you do like any sort of separation? If I say I want to put gas in this already, you see where I'm going?
Yeah, yeah.
Do I have to separate it the like the problem sort of architecture?
No, so actually you can reuse all the simulation problem stuff.
Yeah.
All of that comes in the scheduler and how we're doing the task.
So the schedulers that Automan has is not implicated with the task.
So you can actually use task scheduler if you want, but you have to report the guts of our scheduler and implement put a task. I didn't do that because task it got popular after 2018. And I never went and changed this. But I think the task is also a massive dependency area. Not that it's a bad dependency, it's a big thing. For us it's like brain dead. It's just exact thing. But task is a nice the other thing is task also should work. Task tends to treat every task, every Python function as a task.
Yeah.
Whereas here I'm talking about an entire program that's but I think you could retrofit that into task, just do a Python subprocess and run your program. Task checkpoint was meant more for massive distribution of resilient tasks.
Just right now, so we deploy our software on boats.
Oh,
Like actual boats on the ocean.
oh okay, actual modes. Okay, okay.
So I was, because we use like prefect on top of Dask, and prefect is sort of a scheduler on top of the schedulers, right? But I was thinking of doing something similar to like, because that is more like on the actual deployment side of it. Say a scientist in my lab or who wants to just do this sort of parameters using
time to do it, so that's why.
That's life, so no one pays me to do it.
No, but no one paid us to do this, but yeah, this is it. I think it's useful for everyone, so.
But more of this, right now, no manuals.
Okay, let's see some advanced feature of automan. So for that, first in your code folder, you'll see there is an advanced folder. Move to that folder. So we'll be executing everything inside the advanced folder now. So here's the first thing that in our simulation, some simulations are small tests. So for example, so since I'm from fluid dynamics background, so we have small test cases where we show that our scheme works, right? And then we have the implementation on a real life problem, right? So that the test can take, say, 1 hour, and the actual simulation which we are running on a real life problem can take, say, a day or 2 days. And when the problems are huge, we want to run them parallelly, right? So so there's option. So whenever you are running automan, there is options to first you can pass these options about the computational resource using this particular option, which is ncore and nthread. So ncore is used for scheduling. That means let's say you have n computational resources, and your for every resource you can have, say, 12 cores, some can have 32 cores, and depending upon how many cores your resource have, a simulation can run on that. So let's say on the simulation you specify n core as 10, so n core as 20. So it won't run that particular simulation in a resource which has only 10 cores. And the other thing, which is n threads, is used to specify that how many parallel threads you want the program to run on. So for example, for a 10 core machine, you can have 20 threads for a parallel processing. So you can specify that for all simulations. So let's see how we can do this. So go to this particular file in advanced folder. This is automan num threads. So here you'll see that everything else is as we have done for our power.py file, the automation for that. So here you can see we have a job info dictionary, and if you pass this in the simulation object, and here you can see we are passing n core as 1 and n thread as I for this particular simulation. So, and if you see this particular Python file, let's see that it's just printing the environment variable. So this just prints the environment variable omp num thread, which tells a particular program that how many threads it can use. You can set that. Yeah. So let's try running this as well. So clearly, because nothing is happening, it didn't take much time. So we can just see the output and what it print for. So everything was in standard output. So you can see for all the problems, say for 3, what's the standard output. So you can see that number of threads are set to 3. Similarly for 2, it's set to 2. So if you have a code which can run in using OpenMP, then you can use this particular option to set the number of threads it wants to use. Now let's talk about how we can use Encore. So to use Encore, we should have different computational resources, right? So let's see how we can add that. So to add different computer resource, you can use this particular option, which is Python automan, which you have been running this to automate your simulations, and using this -a option and the host name, you can add any remote resource to this particular to your simulation, to your automation. And let's see how it works. So when you run this, let's try running this and see. So your username is PR, right? Okay. So let's first remove. So first remove the output directories and manuscript if and. Okay, and now let's run any automan file. Let's run num threads only, and you add. So for now, since there is you don't have access to any of the remote computer, you can add this your own computer using your username. So your username Prabhu. So add localhost. So this will add this computer only as a remote computer. So you'll see where it's running by, and also you have to type your pass. So when you run this, there are a few things that you should note, that to run to access a remote PC, you should have an account there, right? So like I have typed Prabhu. So Prabhu is the account name, and add the IP address of the remote PC. So right now it's localhost. That means this particular local computer, and you should have a passwordless access, because let's see what happens when we enter this. It will ask for the password. Okay.
Yeah, because of strict localhost, I have to edit it. So.
Okay. So. So also, if you are using a Mac, you have to allow remote login. Go to your properties and you have to allow remote login. Otherwise, it won't work.
So run this again.
Yeah.
Okay. So yes.
So if you don't want, because we are not doing much here, I'll just show what you should expect.
Okay. Okay. Something went wrong.
Yeah. So here are a few things that this particular command is doing for you. So first, it downloads. So it's not showing up. So let me just show you. Yeah, it's here. Yeah. So first, it downloads this virtual environment.pyz file. So this is a zipper file which you can use to create an environment. So this will be used to create an environment in your remote PC, right? So first thing, it's downloading that particular file. So you need an internet connection. You cannot be just in the local network, or you can keep this particular file in your local directory in .automan. If you have that, then it won't download. So start automan. So it checks for this particular file. If it's not here, then it requires internet. You cannot be in the local network only. And then there are two more files. It first generates. So it's written inside the code base. So it generates these two files for you, and copies these two files to your remote PC, and then it runs this bootstrap. So bootstrap is nothing but it's creating the environment for you, and you can also add a requirements.txt. So let's look at this particular file. So it's first creating an environment using the folder, whichever folder you have used to your automan is kept. It copies everything inside that folder except that output folder and manuscript. And then after creating the environment, it activates the source and then installs automan and install everything you have written. So there are some libraries that you may require. So you may require NumPy and Torch and whatnot for your research. So whatever you need, you have to keep all those inside the requirement.txt, as we have in all Python libraries. And this update, it copies everything. Every time you are running automan, you have to update the source file. So let's say after one run, you find out some mistake in your implementation, you fix that, and then you want to copy these files, and you don't want to run the you don't want to recreate the environments in that remote host. So you can do that by passing some commands, but this particular file just copies the source code from your local PC to the remote PC. So this is all which is happening here.
This doesn't copy it, minus u.
Yeah, this is just the file which helps in that. It updates the this thing. So if you go through again, you will see some options. So this is the option which we have used, -a. This is adding a host to your config file. So I'll show the config file as well. Then you can also specify a particular config file. So config file has the information about the remote PC, whichever you have added. If you want to add some more PC, and these are some PCs which already have environment, you can directly add it. So directly copy it from somewhere from your old automate directory. You can use that same config file, and or you can specify that config file. You can while updating files, you can also pass these options where it won't rebuild your environment. And you have to pass these -u options when you want to copy your source files to the remote machines. And sometimes you find out that you made a mistake and you have to kill the process in all your remote PCs. And then it's a headache to remove all the outputs, because remember that if output folder is present, it won't run that simulation. First thing, and second thing, if you in between you kill a simulation using your task manager, then automan always thinks that it's still running, and it won't run it again, and it shows error. So I think I can show that what error it shows. If I run this, I think because it's not generate. Okay, so here it requires NumPy, so we can show. Yeah. Yeah. So localhost has NumPy installed, so it ran here, but when it ran in Prabhu at localhost, so it created a new environment. To access see the new environment, you can see .domain. Here it created this environment. So this is the new environment it's accessing. And here we don't have NumPy installed, so to install NumPy, you have to create a requirements.txt and just add NumPy here. Yeah, so So can we pass the existing environment? Yes, you can, but not through automan. So if you have your environment, you can copy it using by zipping at. So there are set methods for that.
Can you put it in the actual command? Like
The cop. Yeah,
So
but
what-
the
want to activate and then your Python command will activate.
We don't right now.
Yeah, so basically, you can create an environment, go to your remote and create your environment. If environment created once, you don't have to do this every time. You just run your local host, so your automan file.
Yeah, so just to add to that, so what we do is usually first time when you set up your cluster, your automan cluster, you do -a, and it create -a whatever
Yeah,
host.
that's what I was showing.
Then you play around. Sorry, you set it up in a way that all the requirements you edit, you your requirements, you adjust everything so that that environment is set up just right, and then it just becomes a worker that you just keep using. So it's a one-time cost, but then the machine is there. Yeah.
Yeah, so that's what I was showing. So if you see the config.json, so if you have not done it, so it will just show this first local host. So if you do it once, every time you do it, it will keep on adding it. So if you do a mistake, then it's again adding it. So so if you want to rebuild, you can just rebuild it instead of writing minus everything. Doing minus a adds this every time, right? So you can actually remove one of them. Okay, I'll again threads.
No, you first minus you. So now what he's changed the requirements. So he's going to do a -a.
So it's going to rebuild. It's downloading NumPy because I added that in the requirement.txt.
So technically it's done this on the remote.
Hmm.
We also support Conda environments. So you can do the same thing.
Okay. Yeah. Now let's get back to. So what this added resource is going to, so how it's going to be used. So it depends how many cores your remote PC has, and automan compares that with how many you require. If you require less than that, then automan runs a simulation in that remote PC. And whenever the simulation is complete, then automan copies the output to your local PC. So the benefit is that the remote PC is just used as a computational resource. Your final post-processing and all the output data comes back to your local PC. Yeah, you can also add that option. So let me show that. So there is another option to add NFS. So it's a shared file system that you can add. So this we are not showing.
If your home directory is shared, you don't want it to go create another environment there. So then what you do is you just pass -nfs, so it won't copy anything. It'll assume that the files are local.
Yeah. So, do you want to say
So
it
I'll
here?
just repeat.
Okay.
The mic inside. So basically, if it's on many clusters, you have the same NFS home is shared. So you don't want to copy SCP files back and forth because it's already sitting on the same thing. And you sometimes, if you did that, you may also delete the files because you think it's a remote, but it's actually local. So if you pass --NFS, it will treat it as if that file system, it will never copy anything into it. So, yeah.
Okay. So this we have. So make sure you have a password that's login access to those remote PCs when you are adding this. Otherwise, you every time you have to input your password. That's of no use. Then, yeah.
We haven't put any slides here about how to set up a Conda environment, but it's there in our documentation. It's like when you instantiate the automator, you have to just say use a Conda environment or something like that, and then it'll by default create Conda environments on the remote. And the update script is also, instead of doing pip, you can do pip, it's a script, so you can do anything you want, but you can also put Conda requirements into that.
Yeah, so automan can be also used within a cluster. So this automan was not built for clusters, but we were able to use it. But the only point is that I think it's a good point, because you have to be in a queue to run your simulations in a cluster. So once it captures a particular compute node, it runs everything in that compute node. So in that way, it's good, because you don't have to wait for each simulation. Here is an example of a PBS file, that how you can run on a cluster. So this is what we use. So here there's only 2-3 things that is which I want to emphasize. So first thing is that how many cores you need from the cluster. So you can specify that here, and then depending upon what kind of cluster is that, so they have different structures. So this is one. And you have to also create a Python environment as you do for any simulation in remote PC or your personal local computer. Same as that, you have to specify the particular environment you want to use, and then run your automan file. And it does the same thing. It runs everything, copies the dump to your login node there. Then you have to copy it to your local. So it won't copy it to your local PC, because it works like that only. Yeah, so you can also use automan in ML and AI examples. So automan is not really built to build a ML model, to develop and analyze ML models, but you can use it. There are features which usually we need, like parameter sweeps that Professor Prabhu discussed. So here, so for example, in a neural network, we have neural network width, how many neurons in a layer, how many layers, what are the activation functions, and how many test samples, how many training samples. So those we can specify, and it's like you may use it for development, but it's not built. It's built for numerical methods in general. It can execute, in fact, any kind of executable. But for ML and AI, we have been using it. So I used for my research. I work in ML-based numerical methods. Professor Prabhu has done. There's one published paper on ML and AI. Yeah. And you can, in the post-processing, you can also do different kind of plottings that we discussed. So this is something that we wanted to emphasize, that we can use, and we have been using this for ML and AI as well. Now you can also add arbitrary tasks. So for example, you want to, after all the simulations, you want to compile your LaTeX file. So you can also do that. You can pass using this particular, so this is just an example where you can add create a task. So this is already there. Okay. So this particular class is already there, where you can build a task and then add that to the automator. And then you can also, so there are 3 arguments, where first is task, and another one is the name. So this name you can use to execute just this particular task while running automan, same as you can run any problem at a time. And the last one is post-proc. So this particular the true and false, you can pass any function so that it checks when to run it. So you can pass a trigger to this. So when to run. So for example, you can set that after running all the simulations, then run it. So you can set that in that way. Yeah.
Is this file then has to do the mapping between the problems, like the problem inputs and then
So So the question is that this file command need access to the output of the simulations, right?
yeah, I'm wondering if it does this like mapping,
One-to-one mapping. So this LaTeX file is something that you write independent of. So you should know where your output and files and everything is there. This has nothing to do with like it doesn't automatically finds out where output is, right?
But I mean, like, there are usually images or like image paths attached to the LaTeX file that is to be built, right?
Mm-hmm.
Does it do any mapping between that path and then the output maybe of the PNG path?
This is just a, instead of having a separate make file or something, it's just a way to run an arbitrary task you want to run and deal with it. Otherwise, what ends up happening is you have a automate and then you have a separate make file. It's like a phony task. It doesn't. There's no. The only dependency is if you say postprog is true, you will run this after it finishes everything. Okay. But if you say, I forgot.
Yeah, postprog is for that only. So
If you say it's leave it as false, it's just a task. So you want to just run something. That's it. So it's not. It doesn't do any dependency checks at this point. There's a way by which you can add dependencies,
yeah.
but
Hmm.
this is not. That's
Okay. So we can also automate non-Python programs. So far we have seen examples where we are automating Python programs only. So we'll see one example which is already there in the advanced folder. So we'll automate that particular, so that's a C++ program that we are going to automate using it's automan._c.py file. So let's see that file. So go to your advanced folder. You will see power.cpp. So right now it's not doing anything. It's just reading an input file and printing the input directory, input file name and the contents of that file. So let me go through that. So let me just run. So you can see this particular executable is created, power.out. Now when you run this with this particular input, it will print start and the input file name and the content of this input file. So you can see the input file. Contents are mydir and 2.4. It prints that and then prints end. Simple. So you can create any complicated input file and any complicated CPP file where you are doing something which is useful, right?
maybe you can show them.
Yeah. So so this is the CPU file. Here I am taking the arguments from the command line, and then in C++ there is no, so you have to write your own parser or you have to use some library for that. So it's not that straightforward. So you have to know what the file contents are. So I'm reading this file content. So first, whatever is the first line is my output directory. The second line is the power, and then I'm saving that in those variables and then printing them here. After that, I'm printing end. So this is what I'm doing in this C++. So basically, in C++, you can use input files to pass any data, and you just have to take care of one command line input. So now the problem is we have to create an input file for different simulations, right? So let's go through. So this is same as we were doing before, but now the input is not the the command line does not work as in case of Python files. So in Python files, we were able to pass -t output directory and then other parameters in the simulation. But here we want to pass the after the executor, we want to pass the input file. So this is I am doing it. So you can also do differently, but the ultimate aim is that the input file name should be here after the executable, and after creating all the simulations, I am creating the input. So since the all the these simulations have the access of these simulation paths. So therefore, first we have to create the simulations, and then after creating the simulations, we can create input files for each simulation. So in this function create input, I am doing that. So you can see for using the simulation path, I get the directory name, and then for each directory I am creating these input file names, and the input file I am creating those particular input I need as well. So the directory name and the power. So these are all some what is power? So power is whatever I am passing to this function, right? Any doubt about this? So you can create anything you want using this kind of. So there is no set way of doing this. You can do this differently, but the main thing is that you have to create simulations to get access to the simulation folder. Now let's run this. Also, I'll remove my config file because that has the remote. So you can see it's running this particular command, which is the executable and the input file. So input files are created inside those simulation directories. So now let's see what are the content of these files. Power, let's see any of them, 3. So this has the directory name and this 3. So this is coming in the same line, but this 3 is the power value that we want. Similarly for some other say 2, this is outputs power 2, and 2 is the input for power. And we can also see one of the output. Let's see if the output is as we expected. So it should print start and start the input file name, the directory name, the input of that, and end. Similarly for another simulation, it did the same thing for that. So I have shown that you can use automan for any other language as well. In some cases, we have problems which depends upon another problem. So, for example, we have some tasks. So, let's say we want to attend this workshop. So, but this attend this workshop depends upon registration, right? So, it's a dependency. So, we have to complete the registration, then only we can attend this workshop. So, similarly, I have created this for this power.py. I have created two dummy dependencies. So, we'll see how we can add dependency in a problem. So, let's see this file. So, there are three problems. So, I am running. So, first thing we should note that I am running just one problem, which is powers, and I have not added any other problem which I have created here, pre-calc and pre-calc and power pre-calc. So, this short is just pre-calculations for powers, and power pre-calc for pre-calculations, right? And to add a dependency, we have a function get requires. So, get requires, if you are defining this function, then it should return all the tasks. So, therefore, we have to get all the tasks from the original problem and any tasks we have, any tasks from the problems we have added. So, I have added the dependency for this power problem is power pre-calc. This is a dependency. So, I am adding this particular task to my collection of tasks and returning this in get requires. And let's see what's inside powers pre-calc. So, I am running a simple command here. So, we can run any script here. But here, I am adding another dependency. So, this depends upon this particular problem, right? And similar to the previous thing, I have taken all the tasks of this particular problem and added the task of pre-calc in this get requires. And the pre-calc does not have any dependency, right? And thing to note is that I am just adding the main problem here. The dependencies are not added in the automator. So, now let's see how it looks when we run it. Okay, white one. See, first the pre-calc run, then the pre-calc run, and then the final problem that depends upon these two problems. So, this was a simple example. So, since they were not doing anything, it ran very fast. But usually, if it depends upon some problem, the other problems, even though you have free resources, it won't run the other problem unless the dependent problem finishes. So, now that ends the advanced section. Now, we have time. So, you can take up your current research problem and we'll help you to automate that. So, how we'll see that how we can automate your particular research problem.
Yeah, so Pawan, you can also come. So, we are basically done with the material. There's a little more stuff that's there on the website for the documentation, like details about how to set up a Conda environment, even the dependencies. If you want to look up more, you can read up on the automan documentation. But I think this is enough at this point. So the point now is there's no more material we're going to cover, but if you have something that you want to work on, we can sit with you and help you automate your stuff. So if you have a paper that you're working on, we can sit with you. So the next half hour, we can help you with that, or next 20 minutes. You don't have half hour. So thank you very much.
Yeah, and even if you don't have your research problem with you, you can always create a problem which is the simplest problem in your domain, and create a command line interface for that, and use automan to just create a simple plot for you, and then you can build on that. So we usually start a research paper like that only. So
Yeah. So thank you, and I hope this was useful. But we'll be around to help you around next 20 minutes.